are starting to suspect reality isn't a solid stage at all. It's a fragile agreement, an information scaffold balanced on a false floor. And if that floor ever fails, it won't just destroy worlds, it could erase the very rules that let anything exist. So what if the universe is only metastable, held together by observation, constraints and relationships, and the moment it slips, you won't even have time to be afraid? In the deepest equations of physics, solid ground is a convenient story, one the math no longer guarantees. If the foundations are negotiated, not given, then existence has terms, and terms can be broken. Look closely at the world, and it seems dependable. Clocks advance, atoms hold, stars burn with ancient patience. Yet modern physics keeps uncovering cracks where certainty should live. Places where the universe behaves less like a thing and more like a condition. This film follows a disturbing line of evidence that begins with empty space and ends with a question about facts themselves. Not facts as we report them, but facts as the universe is allowed to possess. What can be recorded, what can be shared, and what must remain forever private. We will move through the vacuum as a physical system, through energies that ought to be enormous but appear almost absent, and through a strange near balance in the numbers that define our cosmos. Along the way, we'll meet a scale of possibilities so vast it reads like fiction, until you see how naturally it emerges from serious theory. Then the story turns inward, to the edge where cosmology and quantum mechanics collide, where time becomes hard to define, and before becomes a word with no obvious anchor. In that region, the universe is not described as evolving in time so much as satisfying constraints, and our familiar sense of history becomes something that has to be earned. From there, we confront boundaries that are not merely horizons in space, but limits on information itself. Black holes, entropy, and the geometry of space-time begin to look less like separate topics and more like one message repeated in different languages. What exists is what can be consistently represented. And finally, we arrive at the measurement problem, the point where physics stops pretending observers are irrelevant. What counts as an outcome, what counts as a record, and what counts as a shared reality may depend on relationships, not proclamations, and the world may be the stable pattern that survives those relationships. This is not a tour of speculation for its own sake. It is a guided descent through real results, real tensions, and real experiments that force an uncomfortable possibility. The origin of reality is not a first moment, but a set of constraints that keeps coherence from unraveling. If that sounds abstract, it isn't, because those constraints decide whether there can be atoms, chemistry, memory, and meaning. They decide whether the universe can host a story at all, or only the silence that follows when the bookkeeping fails. So we begin where physics is most confident, and we keep walking until confidence becomes a hypothesis. Somewhere ahead, a different picture of reality waits, one that does not ask for belief, only for attention. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey, from vacuum stability to cosmic accounting, from a landscape of laws to a timeless equation. Each chapter tightens the same knot. By the end, you won't just ask what reality is, you'll ask what it takes for any reality to hold. Imagine the end of the world as a perfect quiet, the kind of silence that feels too clean to be real. No fireball, no warning sirens, no last message, just a sudden absence, like a film cut mid-frame, leaving only darkness where continuity used to be. A bubble forms somewhere in the universe, perhaps in a void between galaxies where nothing seems to happen. It is not made of matter, and it is not a cloud of particles. It is a change in the vacuum itself, an abrupt shift in the lowest energy state of the fields that fill space. In the language of physics, this is a phase transition, but not the familiar kind that turns water into ice. It is a deeper transition, one that changes what empty means. The vacuum you live in is not just a backdrop. It is a physical medium with a particular configuration. The bubble wall expands at essentially the speed of light, not because it is propelled like an explosion, but because it is a boundary between two stable conditions. It does not push air, and it does not shove matter aside. It replaces the rules. Every atom in its path is forced into a new set of constants, as if the universe has swapped out its operating system in a single frame. Chemistry becomes something else. Structure fails before it can react. The bonds that hold molecules together do not break in the usual way. They become undefined under altered particle masses and force strengths. You would never see it coming because no signal can outrun the front, and there is no advanced shockwave to carry information. Light cannot warn you because light is trapped behind the same limit. The first notice is the moment you are already gone. This is the nightmare hidden inside a technical phrase, spoken softly in seminars and written plainly in papers. Vacuum decay. It sounds like a slow leak, but the scenario it names is instantaneous from your point of view. We call empty space a vacuum, but physics does not treat it as nothing. The vacuum is the lowest energy state available to the fields that fill the universe, and lowest here means something precise. It is the configuration that minimizes energy while still obeying the quantum rules that forbid perfect stillness. Even when fields are in their vacuum state, they are not truly silent. Quantum fluctuations still ripple through them, briefly borrowing energy in accordance with uncertainty. That restless baseline is what makes the vacuum feel eerie to physicists. Emptiness is active, and it has structure. Fields are not just mathematical tricks invented to make equations work. They are the underlying substances that can be excited into particles, and they extend everywhere, even through regions that look empty. You can think of them as continuous ingredients of reality, with particles as localized vibrations. An electron is an excitation of the electron field, a stable pattern that carries charge and mass. Light is an excitation of the electromagnetic field, a traveling disturbance that can cross interstellar darkness. Empty space is the state where those fields are quiet, though never perfectly still. The most famous field in this story is the Higgs field, which is not a particle floating through space like dust. It is a value present everywhere, a background that permeates the cosmos. If you could visualize it, it would not be a cloud, but a universal condition, like temperature filling a room. For decades, it was an idea with consequences, but no direct confirmation. A proposal that explained why some particles behave as if they have inertia. In the 1960s, several teams built the mechanism in parallel, and it became part of the Standard Model's architecture. Yet for years it remained a missing pillar, necessary but unseen. Then the Large Hadron Collider found the Higgs boson, a fleeting resonance produced in high-energy collisions. The discovery was not only a triumph of engineering and statistics, but also a confirmation that the field is real. You do not find a ripple without something that can ripple. The Higgs field matters because it sets the masses of fundamental particles. And mass is not merely weight. Mass determines how particles move, how they bind, and whether stable atoms can exist at all. A universe with different Higgs behavior could have no chemistry, or chemistry too alien to build structure. In the Standard Model, the vacuum depends on the Higgs potential, a function that tells you the energy cost of different Higgs field values. That potential is like an energy landscape for the Higgs field's value, a terrain of hills and valleys. The vacuum is where the field naturally settles, like a marble rolling until it can roll no farther. If the landscape has one deepest valley, the vacuum is absolutely stable, and the story ends there. If it has a lower valley separated by a barrier, the vacuum can be metastable, and the story becomes tense. Metastable means stable in practice, but not guaranteed forever. Metastability is not a poetic term, and it is not rare in nature. Supercooled water can remain liquid below freezing until a disturbance triggers crystallization, and some materials can sit in long-lived states before snapping into a lower energy arrangement. The unsettling twist is that we are applying that logic to space itself. Picture a ball resting in a shallow valley under a night sky, with a deeper valley hidden beyond a hill. It can sit there for an extremely long time, and nothing about its stillness proves it is in the lowest place. The stability you observe may be only the stability of a trap. Classically, the ball cannot cross the hill without a push, because energy must be supplied to climb. Quantum mechanics allows a stranger option, one that defies everyday intuition. Tunneling. Tunneling means the ball can appear on the other side without climbing over, because quantum objects are described by probabilities spread across space. The probability can be tiny, but time can be enormous, and in cosmology, enormous time is the default. Given enough time, even rare events become relevant questions. If the Higgs vacuum is only a local minimum, then the universe is balanced on a false floor, and the floor is not a metaphor. It feels solid because it has held so far, and because every experiment we run is conducted inside it. But the equations allow the possibility that the real ground is lower. A true vacuum would be the deeper valley, the global minimum of the potential. A transition would nucleate a bubble of that lower energy state, a region where the Higgs field takes on a different value. Nucleation is the key word. Decay would not happen everywhere at once, but would begin locally. Inside the bubble, the Higgs field settles into a different value, and that change would alter particle masses and the strengths of forces. Even small shifts could cascade into huge consequences, because stable matter depends on delicate balances: the proton's stability, the electron's mass, the range of the weak force. These are not independent facts. The bubble wall would be a boundary between two realities, thin compared to cosmic distances, but decisive in its effects. It would move outward, converting space as it goes, and it would not slow down for stars or planets. There is no friction with the old vacuum, because the vacuum is not a substance you can plow through. This is why the apocalypse is quiet, and why it is so hard to dramatize honestly. There is no time for light, neutrinos, or gravity waves to warn you ahead of the front. Whatever information could be carried by those messengers is limited by the same speed limit the wall nearly matches. The dread is not only speed, though speed is enough. It is that the vacuum is the stage for every event, and the stage itself may be temporary. We are used to thinking of physical law as eternal, but here law becomes conditional, dependent on which vacuum state the fields occupy. For a long time, this sounded like a speculative horror story attached to equations, a clever way to make people shiver during a colloquium. Then measurements sharpened, and the equations started pointing somewhere uncomfortable. The fear did not come from imagination alone, but from numbers. The Higgs mass is about 125 GeV, and that number is not just a particle property measured in a detector. It feeds into the shape of the Higgs potential at high energies, because quantum corrections depend on it. In quantum field theory, what you measure at one scale influences what you infer at far higher scales. Another number matters even more, and it carries an almost unfair weight: the top quark mass. The top quark is the heaviest known elementary particle, and its heaviness means it couples strongly to the Higgs field. In the equations, it leans hard on the potential. Through quantum effects, the top quark pulls on the potential and can tilt the landscape, changing whether the Higgs self-coupling stays positive. The details are technical, but the plain language version is simple. Heavy particles can destabilize the vacuum by reshaping the energy landscape through loops and corrections. In quantum field theory, couplings run with energy, meaning their effective values shift as you probe shorter distances and higher momenta. This is not an optional feature, but a consequence of renormalization, the bookkeeping that keeps infinities from ruining predictions. The effective Higgs self-coupling changes as you climb the energy ladder. When physicists combine the measured Higgs mass, the top quark mass, and the running of couplings, they can extrapolate the potential far beyond collider energies. They are extending a map into territory we cannot directly visit, using the rules we trust. It is powerful, but it comes with uncertainty, like forecasting weather on a planet you have never seen. That extrapolation suggests a disturbing possibility. The Higgs potential may turn over at very high scales, making our vacuum not the deepest one. The phrase "turn over" sounds gentle, but it implies the valley we occupy could be perched above a deeper drop. The result is not a clean verdict, and it is not a headline that can be settled by one more decimal place. It is a placement on a map, with error bars that matter. On that map, there is a region of absolute stability, where the potential remains safely shaped. There is a region of metastability, where a deeper vacuum exists, but the barrier makes decay extraordinarily unlikely. There is also a region where the vacuum would already be unstable, implying a rapid decay that clearly has not happened. The fact that we exist rules out that last region, but it does not tell us which side of the boundary we inhabit. Current best estimates put us near the boundary between stability and metastability, and that is the strange part. Not deep in safety, not clearly in danger, balanced close to a line. The universe seems to have chosen parameters that land in a narrow corridor rather than a wide open plane. This boundary is sometimes called a knife edge, and it is not poetic language added for drama. It is a statement about how sensitively the conclusion depends on measured inputs, especially the top quark mass and the strong coupling constant. Small changes in those values can shift the entire interpretation. A small shift in the top quark mass can move the universe from stable to metastable, at least within the standard model's extrapolation. A small shift in theoretical corrections can do the same, because higher-order calculations refine the running couplings. This is why particle physicists obsess over calibration, systematics, and what mass even means in a quantum theory. So what is actually known and what is only suggested by extrapolation? We know the Higgs field exists, because the Higgs boson was observed with clear statistical significance. We know the standard model lets us compute how the Higgs potential behaves as energy increases. And we know those computations depend on precise parameters. We also know that those parameters are measured with finite precision, and that translating detector data into a top quark mass involves subtle definitions. The top quark decays almost instantly, so you never weigh it on a scale. You infer its mass from the patterns of its decay products, and inference always carries assumptions. We know the measured values are consistent with metastability, and that consistency has survived years of scrutiny. We do not know whether the true vacuum exists in nature, or whether new physics changes the story before the dangerous scales are reached. Even a small new interaction at high energy could reshape the potential and stabilize it. Metastable does not mean imminent doom, and it does not mean the bubble is lurking just beyond the moon. The calculated lifetime of a metastable vacuum can be vastly longer than the age of the universe, longer than stellar lifetimes, longer than the time it takes galaxies to drift apart. In many estimates, it is so long it becomes almost abstract. Even if decay is possible, it may be so rare that it effectively never happens here. Probability can be non-zero and still irrelevant on human timescales or even on cosmic timescales. Yet the knife edge itself is the story, because it raises a question that refuses to go away. Nature did not have to choose numbers that land near this boundary, and nothing in the basic equations demands that it did. If the standard model is complete up to extremely high energies, then our vacuum looks like a temporary arrangement that happens to last. If the standard model is not complete, then something else is holding the floor. Either way, the vacuum stops being a passive background and becomes an active question about why reality is this way and not another. The emptiness between galaxies becomes a physical object of inquiry, with properties that can be stable, unstable, or delicately balanced. The universe, in this view, is not merely evolving in time, it is sitting in a state. This is where the documentary's tension begins, because the stakes are both existential and conceptual. Is the universe built on stable bedrock, or on a metastable configuration maintained by hidden constraints? And if it is balanced, what selected the balance? Blind chance, deep symmetry, or something we have not yet measured? The false vacuum idea also forces a deeper shift in perspective, one that can feel almost philosophical even when expressed in equations. What we call laws of physics may be properties of a particular vacuum state, not timeless commandments. Change the vacuum, and the laws change with it. The constants we treat as fixed may be contingent outcomes, like the freezing point of water depends on pressure. The speed of light as a limit remains, but the character of matter could be rewritten. Would atoms even exist in a true vacuum? Or would the very notion of particle be replaced by a different spectrum of excitations? That possibility reaches beyond apocalypse scenarios, and it touches the meaning of explanation in physics. If our vacuum is not uniquely selected, then why do its parameters sit where they do? Why this Higgs mass? Why this top quark mass? Why couplings that nearly destabilize everything? Some physicists see coincidence, a numerical accident with no deeper cause. Others see selection effects, multiverses, or new symmetries that stabilize the potential without our noticing. But before any of that, we have to face the simplest unsettling claim, stated plainly and left to echo. The emptiness between galaxies might be a metastable state, not the final ground. The vacuum is the lowest note the universe can play, the baseline hum beneath every process. If it is not the lowest possible note, then reality is a chord held by chance, and chords can resolve. And if a lower note exists, the transition is not gradual, not a slow drift of constants over eons. It is a bubble that expands at light speed, rewriting physics with no warning. The universe would not end with a bang, but with a clean edit, a cut from one set of rules to another. So the first question is not whether we should panic, because panic is useless against a light speed boundary. The first question is why the floor is even allowed to be false, and why the numbers place us so close to the edge. Are we seeing a clue about deeper physics, or a coincidence written into our existence? From here, the story turns from catastrophe to cause. If the vacuum is contingent, then we must ask what sets the parameters at all, and why they appear tuned to sit near critical lines. That leads directly into fine-tuning, where why becomes quantitative and uncomfortable. It leads into the largest discrepancy in physics, where theory predicts one vacuum energy and the universe shows another, and the mismatch is not small. To understand whether reality is stable, we have to understand why it is balanced. To understand why it is balanced, we have to measure the mismatch beneath everything. From here, the story turns from catastrophe to cause. The false vacuum is terrifying But the accounting behind it is worse, because it reaches into the definition of nothing, and then asks whether nothing can ever truly be neutral. We call empty space a vacuum, but physics does not treat it as nothing. In quantum field theory, every field has a ground state, and that ground state carries energy, even when no particles are present. On screen, the vacuum is often drawn as blackness, a clean stage awaiting actors. In modern physics, it is closer to a restless ocean at midnight. Dark, apparently calm, yet never truly still. The unsettling part is not that the vacuum has energy. The unsettling part is that the vacuum energy should be enormous, and the universe behaves as if it is tiny, almost as if a vast bill was never paid. Vacuum energy begins with a simple rule that never lets fields fully rest. Quantum uncertainty forbids perfect stillness, even in the lowest possible state, and it does so with mathematical stubbornness that survives every experimental test. Heisenberg's uncertainty principle is usually taught with particles and positions. In field language, it becomes a statement about amplitudes and their conjugate momenta. Squeezing one makes the other spread, and the vacuum can't be pinned down. A field is not a particle, but a continuous ingredient spread through space. Particles are excitations, and the vacuum is the configuration with no real excitations present, like a guitar string that is not plucked. Yet even an unplucked string can tremble from thermal noise or a passing vibration. Quantum fields do something stranger. They tremble even at absolute zero, because the rules of measurement forbid complete silence. Even without particles, the field still fluctuates around its minimum. Those fluctuations have a baseline energy, often called zero-point energy, and they are not optional features we can turn off. In a harmonic oscillator, the lowest energy is not zero. Quantum mechanics leaves a residual half-quantum, and field modes behave like oscillators at every wavelength, from cosmic scales down to the smallest we can meaningfully discuss. Visually, imagine space tiled with invisible springs, each one capable of vibrating. Every wavelength is a different spring. Even when none are excited, each retains a minimal jitter that contributes to the vacuum's ledger. So the vacuum is a sum over modes, each contributing a small minimum energy. Add infinitely many modes, and the naive sum diverges toward infinity, because there are infinitely many possible wavelengths. This infinity is not a poetic exaggeration. If you integrate the zero-point energy over all momenta, the result grows without bound, and the growth is dominated by the shortest wavelengths, those that pack the most oscillations into the smallest space. When the camera pulls back, you can picture those wavelengths as a spectrum fading into the ultraviolet. Each step to shorter scales adds more modes per volume, and the bookkeeping accelerates, as if the vacuum were hiding an endless reservoir of microscopic motion. Physicists do not accept infinity as a literal prediction of nature. They renormalize, subtract, and redefine, because only energy differences are measurable in many settings, and many experiments never ask for an absolute zero. Renormalization is often described as sweeping infinities under the rug. A better image is bookkeeping with a reference point, choosing what counts as zero, so the remaining measurable differences become finite and predictive. That move works spectacularly well in particle physics. It predicts magnetic moments, scattering rates, and atomic shifts with extreme precision. And it does so in ways that match experiments to many decimal places. The Casimir effect gives a rare, tangible hint of vacuum structure. Two metal plates placed close together feel an attractive force, because the allowed field modes between them differ from the modes outside, and the difference shows up as a measurable push. On screen, the plates can be shown as two dark mirrors in a clean laboratory glow. Between them, only certain wavelengths fit, like notes allowed in a narrow organ pipe. so the vacuum outside presses harder than the vacuum inside. In that sense, vacuum energy is not merely a philosophical claim. It leaves fingerprints when boundaries or materials restrict fluctuations, and those fingerprints can be weighed, however delicately, in the laboratory. Gravity, however, refuses to ignore the baseline. In general relativity, energy gravitates, and a uniform vacuum energy acts like a pressure-filled substance everywhere, even when it has no particles and no temperature. A constant vacuum energy density curves space-time even when nothing else is present. In Einstein's equations, it appears as the cosmological constant, written as L, a term that looks deceptively simple. Historically, L entered the story as a patch. Einstein introduced it in 1917 to allow a static universe, then later called it his greatest blunder after cosmic expansion was discovered, though the quote itself has a complicated history. The deeper point is that the term never truly went away. Even if Einstein regretted the motivation, the mathematics kept the door open, because a constant term is allowed by the symmetries of spacetime itself. Yet L is not merely a number added for convenience. It is the simplest term consistent with spacetime symmetry, and it behaves like a constant energy density of empty space, the same in every direction. In the language of relativity, vacuum energy has an equation of state. Its pressure is negative and equal in magnitude to its energy density, a relationship that makes gravity behave counterintuitively on cosmic scales. Negative pressure sounds like science fiction, but it is a precise statement about stress energy. In plain terms, as space expands, vacuum energy does not thin out, so the expansion can feed on itself, like a stretching fabric that never loses its tension. If vacuum energy is large, space-time should curve violently. The universe should either expand explosively or collapse quickly, leaving no time for structure, chemistry, or the slow assembly of galaxies. The visual implication is stark. A large L would make the cosmic web never form, leaving matter smeared thinly across space, or else it would crush everything back into a rapid, premature end. Yet the cosmos we observe is old, spacious, and filled with galaxies. That calm longevity is the first hint that the vacuum's gravitational bookkeeping is strange, because the baseline seems almost, but not exactly, cancelled. The modern evidence arrived in the late 1990s, when distant Type Ia supernovae looked dimmer than expected. These stellar explosions act as standardizable candles, because their peak brightness correlates with how quickly they fade. Type Ia supernovae are thought to involve white dwarfs pushed past a critical threshold. The details can vary, but their light curves are regular enough that astronomers can infer distance by comparing intrinsic brightness to observed brightness. On screen, the data appear as a scatter of points on a Hubble diagram. The distant points sit slightly below the line expected for a decelerating universe. Small deviations, but consistent ones, repeated across many events. What makes those dots persuasive is their stubbornness across teams and telescopes. Different surveys, different calibrations, and different nights under different skies kept returning the same quiet message. Something is making the expansion speed up. The simplest reading was that cosmic expansion is accelerating. It was an unsettling conclusion, because gravity from matter should slow expansion down, not speed it up, if matter were the only actor. Acceleration means the expansion rate is not merely coasting from an ancient explosion. Something is pushing, or space-time itself has a built-in tendency to stretch faster, like a fabric under tension that relaxes by expanding. Supernova data did not stand alone for long. Measurements of the cosmic microwave background fixed the geometry, and large-scale structure mapped how matter clumps over time, providing independent checks. The The cosmic microwave background is a fossil light field, released when the universe cooled enough for electrons and protons to form neutral atoms. Its tiny temperature ripples encode the early balance of matter, radiation, and geometry. Those ripples appear on screen as a mottled oval map. Hot and cold patches only tens of microkelvin apart. From their angular pattern, cosmologists infer that space is very nearly flat, which constrains the total energy density. Large-scale structure adds the third leg of the argument. Galaxy surveys reveal a cosmic web of filaments and voids, and the statistics of that web tell us how quickly matter could grow under gravity. In visuals, the web looks like frost spreading across glass, with bright knots where clusters live. If dark energy dominates too early, that frost never thickens, so the very existence of rich structure becomes part of the measurement. Together, these datasets converged on a consistent picture. Most of the cosmic energy budget is not matter, but something smooth that does not clump like galaxies, and that remains diffuse even as the universe expands. We call it dark energy because it is inferred from gravity, not seen directly. The simplest model treats it as a cosmological constant, a constant vacuum energy density that does not dilute as space grows. In that model, the pressure is negative. Negative pressure is not a metaphor, but a property of the stress-energy tensor that makes expansion accelerate, because pressure contributes to gravity in relativity. A useful plain language translation is this: normal stuff pulls inward, while vacuum energy effectively pushes outward. The push is not like a wind. It is the geometry responding to a uniform energy density. The observed dark energy density is small in everyday units, but it dominates the universe today. It is about 7/10 of the total energy density at present, with matter making up most of the rest. If we translate that density into laboratory terms, it is roughly the energy of a few protons spread across a cubic meter. That is vanishingly small by particle physics standards, yet cosmologically decisive. Here the debt appears. Quantum field theory suggests the vacuum energy should be huge, while cosmology measures a value that is tiny but non-zero, a remainder that refuses to vanish. To express the mismatch, physicists use Planck units, where gravity sets the natural scale. In those units, the observed vacuum energy is roughly 10 to the minus 120, a number so small it barely feels physical. Planck units are built from fundamental constants: the speed of light, Planck's constant, and Newton's gravitational constant. They define a scale where quantum effects and gravity are equally strong, the scale our theories fear and crave. Naive estimates from quantum fields give something closer to 1 in Planck units. The ratio is around 10 to the 120, an absurd gap between theory and reality, as if a calculation missed the universe by the width of the cosmos. This is why it is called the worst prediction in physics. It is not off by a factor of 2, or even a factor of 1,000,000, but by a number with 120 zeros, a mismatch that dwarfs ordinary embarrassment. On screen, the comparison can be shown as a ledger. One column is a towering stack of contributions, rising beyond the frame. The other is a thin line near zero, the value the sky itself seems to prefer. The number is so extreme that it changes how explanation feels. It suggests either a deep principle we have missed, or a catastrophic misunderstanding of what the vacuum is, and perhaps of what gravity counts as energy. The discrepancy is not only about zero-point energy. Every field contributes, and every symmetry breaking contributes, including the Higgs field that shaped Chapter 1, because vacuum energy is sensitive to the state fields settle into. When the Higgs field takes a non-zero value, it changes the vacuum energy. The electroweak phase transition should shift the vacuum energy by an enormous amount, because the Higgs potential carries an energy offset. Phase transitions are not just changes in appearance, they are changes in the vacuum configuration, like water freezing into ice, except the substance-changing phase is a field that fills all of space. In the early universe, temperature mattered. As the cosmos expanded and cooled, fields could roll into new minima, and the vacuum energy could jump, releasing latent heat into particles and radiation. You can visualize that cooling as a bright fog thinning into clarity. As the temperature drops, the field landscape reshapes, valleys deepen, ridges rise, and the universe settles. Not by choice, but by dynamics. QCD, the physics of quarks and gluons, also changes the vacuum through condensates. Those contributions are smaller than Planck scale, but still vastly larger than observed L. And they are not speculative, they are part of the Standard Model's structure. The QCD vacuum is not empty. It contains gluon fields and quark, antiquark pairs in a collective state, and that state has an energy density associated with confinement, the mechanism that binds quarks into protons and neutrons. Even if you try to renormalize away a huge constant, you still face gravity. The value that remains is what curves space-time, and it is the value we measure, because L is not an energy difference between two lab setups. So the problem becomes a question of cancellation. Many large contributions must sum to nearly zero, leaving a tiny leftover that drives acceleration, and the leftover must be stable across cosmic history. That cancellation must be precise to about 120 decimal places in Planck units. It is not the kind of precision that emerges casually from independent physical effects, especially when those effects arise at wildly different energy scales. To picture the required precision, imagine subtracting two enormous numbers that agree in their first 120 digits. The difference is not merely small, it is fragile, and any slight change in either number would overwhelm it. Fine-tuning is the name for this discomfort. A parameter looks unnatural when small changes in underlying physics would make it enormous, unless something enforces the smallness, like a rule that forbids it from growing. Physicists have seen fine-tuning before, and sometimes it points to new symmetry. Symmetry can protect small numbers, the way gauge symmetry protects the photon mass, keeping light exactly massless in the Standard Model. But for vacuum energy, known symmetries do not solve the problem. Supersymmetry could cancel contributions, yet it must be broken, and broken supersymmetry still leaves a large residue far above the observed value. The vacuum energy problem is also not a technicality of calculation. It is a clash between two frameworks we trust, quantum field theory and general relativity, each tested in its own domain with extraordinary success. Quantum field theory says the vacuum is busy, full of fluctuations and condensates. General relativity says any energy density, even uniform, should gravitate and curve spacetime, because spacetime responds to stress energy, not to our intuition. The universe answers with a whisper instead of a roar. Spacetime accelerates gently, as if the vacuum energy is tuned to a value just above zero, and the gentleness is part of the mystery. That gentleness is visible in the sky's timeline. For billions of years, matter dominated and structure grew. Only later did dark energy begin to win, gradually stretching the cosmic web and widening the voids. That timing invites a question that lingers in the background. Why now? Why should we live in an era when the smooth component becomes comparable to matter, late enough for galaxies, but early enough to still be noticeable? This is where Chapter 1 returns with new weight. If the electroweak vacuum might be metastable, then the vacuum is not a passive stage, but an active ingredient, one that can hold tension and, in principle, release it. A metastable vacuum is a local minimum of an energy landscape. The cosmological constant is the height of that landscape, the baseline energy of the vacuum we occupy, and the height matters gravitationally. Energy landscapes are often drawn as rolling hills and valleys. The image is useful because it captures both stability and danger. A ball can sit quietly in a shallow dip, yet a deeper valley may lie nearby. If the vacuum can decay, then vacuum energy is not just a number. It is a property of a state, and states can change, sometimes abruptly, when quantum tunneling allows a transition through a barrier. In the false vacuum picture, decay begins as a microscopic bubble. The bubble wall separates two phases of the vacuum, and the wall can race outward at nearly light speed, converting space itself as it goes. That connection deepens the mystery. The same vacuum that might be perched above a lower valley also seems to have an inexplicably small baseline height, as though the landscape was engineered to hover near zero. In the false vacuum picture, a lower vacuum might have a different L. A bubble of true vacuum would not only change particle masses, but also change the curvature of space-time, because vacuum energy is a source in Einstein's equations. So the apocalypse scenario gains a second dimension. It is not only that constants could change, but that space-time itself could reconfigure, because the vacuum energy sets expansion and, in extreme cases, the causal structure of the region. A useful visual is a grid drawn on space, like graph paper. In one vacuum, the grid stretches gently. In another, it might stretch violently or curl inward, and the bubble wall is the moving boundary between those geometries. This is why the discrepancy feels like an unpaid debt. The equations demand a huge vacuum energy, and the universe refuses to pay it, yet still pays a tiny amount, as if leaving a coin on a table meant for a mountain of gold. One response is to say, we are calculating the wrong thing. Perhaps vacuum energy does not gravitate in the naive way, or perhaps gravity is modified at large scales, so that uniform energy is screened or reinterpreted. Another response is to say, the vacuum energy is real, but cancelled by an unknown mechanism. That mechanism would have to be extraordinarily rigid, cancelling contributions across phase transitions and doing so without spoiling the successes of quantum field theory. A third response is more unsettling. Perhaps there is no unique value to explain, because different regions of a larger reality realize different vacuum energies, and what we call the constant is local rather than universal. Before that leap, the chapter stays with the tension. If L is small because of cancellation, then the universe looks engineered, even if no engineer exists, because the cancellation resembles a deliberate adjustment. The constants begin to look chosen, not derived. The vacuum looks selected, not inevitable, as if reality is sitting on a narrow ledge of permitted values, with steep cliffs on either side. This is where the central question sharpens. Is reality stable and observer independent? Or is it metastable and information-bound, held together by constraints that could have been different and that might not last forever? Cosmology makes the question measurable. L is not a philosophical preference, but a parameter inferred from data, and it controls the fate of expansion, deciding whether the distant future is dilution, collapse, or something in between. If L were much larger and positive, expansion would accelerate earlier, matter would be pulled apart before it could clump, and galaxies would struggle to form, because gravity would lose the race before it began. The cosmic web would remain a faint fog. Stars would be rare, heavy elements would be scarce, and the long chemical chain from hydrogen to life-friendly complexity might never get started. If L were negative and large in magnitude, the universe could recollapse quickly. Either way, complex structure would be rare, and long-lived observers would be unlikely, because the window for complexity would slam shut. This observation is not a solution, but it is a pressure valve. It suggests that our measured L might be conditioned by the requirement that observers exist to measure it, which is a statement about selection, not mechanism. That idea is called anthropic selection. It does not claim the universe was made for us, but that we can only appear where conditions permit complexity. In the same way, fish only appear where water remains liquid. In this framing, the smallness of L is not explained by a symmetry. It is explained by a filter, where many possible values exist, but only a narrow band allows galaxies, and therefore allows anyone to notice the number. The anthropic argument is dangerous because it can end curiosity. It can sound like surrender, replacing mechanism with a statement about our own presence, and it can tempt us to stop asking what deeper rule might exist. Yet, it also matches the shape of the problem. When the discrepancy is 10 to the 120, ordinary naturalness arguments start to feel too weak, and the mind starts searching for explanations that scale with the enormity. Physicists resist anthropic reasoning because it is hard to test. Still, the data keep pointing to a small positive L, and the theoretical accounting keeps demanding something huge, so the tension refuses to fade. So the chapter holds both facts in the same frame. The vacuum may be metastable, and the vacuum energy may be inexplicably small, and both statements concern the same emptiness, space itself as a physical object. The vacuum becomes a ledger with two columns that will not balance. One column is quantum fields, adding contributions at every scale. The other column is cosmic expansion, measuring the remainder and insisting that the remainder is real. This mismatch is not a minor crack in an otherwise complete picture. It is a sign that our two best descriptions of nature do not agree about the baseline of reality, the very level from which everything else is measured. It also changes how we think about the origin of reality. If the vacuum sets laws and sets expansion, then the origin is not only a beginning in time, but a settling into a particular state among alternatives. The origin becomes a choice of state, a selection of vacuum, and a selection of constants. The disturbing possibility is that selection might be statistical, not fundamental, and that what we call law might be partly environmental. To make that idea concrete, physicists imagine many vacua with many L values. Each vacuum is a different minimum in a larger theory's landscape of possibilities, separated by barriers, like valleys in a mountain range. The visual can widen into a vast topographic map. Peaks and ridges stretch beyond the horizon. Countless basins lie below, each with its own depth, its own baseline energy, and its own version of what empty space means. If such a landscape exists, then our L could be one draw among many. We would find ourselves in a region where L is small enough for galaxies, because elsewhere there are no observers, only sterile expansion or rapid collapse. This is not yet an answer, and it is not yet a theory. It is a direction forced by the scale of the discrepancy and the failure of simple mechanisms, a signpost that points beyond familiar ground. The chapter ends by tightening the link to chapter 1. A false vacuum implies multiple minima, and multiple minima imply many possible vacuum energies. So metastability and the cosmological constant problem begin to share the same stage. If the vacuum is a state, and states can vary, then constants can vary too. Selection becomes a physical question, not a metaphysical one, because it can be tied to dynamics, probability, and cosmic history. The next step is unavoidable. If constants look selected, where could selection come from? And what larger structure contains the options, if not a single, unique vacuum that all of reality must obey? Enter the multiverse logic and the string landscape. The unpaid debt of L becomes the clue that reality may not have a single flaw at all, but many flaws, each one stable for a time, each one with its own accounting. And if there is no single flaw, then stability is not guaranteed. Reality might be a temporary agreement between fields, geometry, and information, holding only as long as the constraints hold. And the quiet acceleration of the cosmos becomes a warning written in slow motion. The universe looks calm because its numbers cooperate, and that cooperation feels suspiciously precise when you stare at it long enough. On the largest scales, the sky seems indifferent: black space, thin galaxies, slow expansion. Yet the equations underneath behave like a lock that opens only for one narrow key. After vacuum decay and the cosmological constant debt, the question sharpens into fine-tuning, and it stops sounding like poetry. Why do the parameters land in the narrow band that permits structure at all, when the broader mathematical space looks hostile to complexity? When we say band, we mean it literally. Ranges of values that allow matter to clump, atoms to persist, and stars to burn steadily. Fine-tuning is not a vibe or a metaphor, and it is not a claim that the universe was meant to be this way. It is a statement about sensitivity, where small parameter changes erase galaxies, atoms, or long-lived complexity. In physics, the disturbing part is not that values are small in absolute terms. The disturbing part is that they seem balanced against enormous competing contributions, as if multiple gigantic terms almost cancel and leave a fragile remainder. Visually, imagine a control room with dials that have no labels, only numbers, and most settings trigger a silent failure. One dial is turned a hair, and the cosmic web never forms. Another dial shifts slightly, and chemistry becomes a brief flicker, not a durable architecture. Start with the cosmological constant, L, the baseline energy of empty space, sometimes described as vacuum energy density. Observations say it is tiny and positive, and it acts like a gentle pressure that accelerates expansion. Yet quantum field theory expects huge contributions from every field, because even empty space is filled with fluctuating modes. Those fluctuations are not philosophical, and they are not optional. In quantum theory, fields behave like collections of oscillators, and even at zero temperature, they retain a residual energy. If you add up those zero-point energies in the naive way, the result is catastrophically large, and it dwarfs what the sky actually reveals. The cosmological constant problem is not merely that theory overshoots. It is that the overshoot is by an absurd factor, and the cancellation required looks unnaturally exact. If those contributions do not cancel with extreme precision, space-time either inflates too fast for galaxies, or it collapses before chemistry can begin. The allowed window for L is narrow because gravity competes with expansion, and the competition has a clear visual signature. Gravity tries to amplify small density ripples into filaments, clusters, and halos. A positive L pushes the other way, stretching space so persistently that matter cannot gather into the scaffolding of galaxies. Raise L by orders of magnitude and matter never clumps into the cosmic web, leaving a thin mist of particles that cools and thins forever. Flip the sign strongly negative and the universe recollapses quickly, ending the story early in a crunch. The measured value sits in the thin region that allows long cosmic time, long enough for stars to forge heavy elements and for planets to remain stable. There is a historical undertone here, because L was once treated as a mistake. Einstein introduced it to hold the universe static, then called it his biggest blunder when expansion was discovered. Decades later, supernova surveys and cosmic microwave background measurements brought it back, not as a patch, but as a measured feature of our cosmos. Now the calm, accelerating expansion becomes a data point with teeth. The vacuum seems to have a small, persistent energy, and the number is not just small. It is small compared to what our best quantum frameworks naturally generate. Then comes the electroweak hierarchy, the Higgs scale versus the Planck scale, and the contrast is almost theatrical. The Higgs vacuum expectation value is about 246 GeV, setting the scale of electroweak symmetry breaking. The Planck scale is around 10^19 GeV, where gravity becomes strong in quantum terms, and spacetime itself is expected to become turbulent. In quantum field theory, scalar masses want to be dragged upward by high-energy physics because they receive corrections from virtual particles at all energies. Keeping the Higgs light looks like another delicate cancellation, as if the bare mass and the quantum corrections nearly negate each other. The Higgs boson's measured mass, around 125 GeV, makes the question concrete rather than abstract. This is the hierarchy problem in its simplest form, and it is about radiative stability. Quantum corrections to the Higgs mass are sensitive to the highest energies that exist in the theory, often represented by a cutoff. Without protection, the natural expectation is that the Higgs mass should be near that cutoff, and the electroweak scale should not sit so far below. Yet the world we measure keeps it far below, and the gap is enormous, spanning many orders of magnitude. That gap is not just a number on a chart, it is the difference between a universe with stable, familiar particle masses and a universe where the weak force becomes radically different. Fine-tuning also appears in the masses and couplings that make chemistry possible, and here the consequences become tactile. Change the electron mass and atomic sizes shift, because the Bohr radius depends on electron mass and electromagnetic coupling. Alter that scale, and reaction rates change, molecular shapes change, and the thermal stability of complex molecules can vanish. Change the up and down quark masses, and protons and neutrons reshuffle their stability, because nucleon masses and binding energies depend on quark masses and QCD dynamics. If the neutron were much lighter relative to the proton, hydrogen could disappear. If the proton were unstable in the wrong direction, the simplest atom could become rare. Change the strength of the strong force slightly, and nuclei either fail to bind or bind too aggressively, and both extremes are sterile. Too weak, and deuterium becomes unstable, blocking the chain of stellar nucleosynthesis early. Too strong, and nuclear reactions run differently, potentially burning fuel too quickly and rearranging the abundance of elements. Even the electromagnetic coupling matters in a way that feels unforgiving, because it sets the scale of atomic binding and the repulsion between protons in nuclei. Increase it and fusion in stars changes, because the Coulomb barrier becomes harder to penetrate. Decrease it and chemical bonds weaken, and complex molecules struggle to persist against thermal agitation. The point is not that life is special, and it is not a covert argument from biology. The point is that structure is conditional, and structure includes galaxies, long-lived stars, stable nuclei, and the possibility of persistent information. A universe can be mathematically consistent and still be physically barren. At this stage, the central question returns with new force, and it carries a faint sense of vertigo. Is reality stable and observer-independent, or metastable and information-bound, held together by constraints that could have been different? Fine-tuning suggests our vacuum is not inevitable, and it suggests we occupy a rare configuration in a larger space of possibilities. Physicists have two broad instincts when faced with fine-tuning, and both are rooted in past victories. One is to search for a mechanism, like symmetry, that makes the small numbers unavoidable, the way gauge symmetry shapes electromagnetism. The other is to accept that many values exist, and we observe a compatible one because incompatible regions contain no observers. The second instinct is selection, and it becomes hard to avoid when the numbers look extreme. It is not a surrender by default, but it does change the flavor of explanation. Instead of deriving a unique value, you ask what values are typical among those that allow structured universes. The multiverse idea enters here as a pressure response, not as a fantasy add-on. If there are many consistent vacua with different constants, fine-tuning can become a filter rather than a miracle. We do not explain L by cancellation in one unique universe. We explain it by distribution across many, with observers appearing only in the narrow band. To make that move credible, physics needs a framework that actually contains many vacua, not just rhetorical room for them. It needs a theory where different low-energy worlds are not merely imagined in a philosopher's notebook. They must be real solutions of the same underlying equations, emerging from the same microscopic rules. This is where string theory changes the frame, because multiplicity is built into its geometry. In string theory, the fundamental objects are not point particles but extended strings, and their vibrational modes appear as particles. Consistency requires extra dimensions, not as decoration, but as a condition for anomaly cancellation and mathematical coherence. Those extra dimensions are not optional decorations, and they are not simply elsewhere in a science fiction sense. They must be compactified, curled into shapes too small to see directly, so that at accessible energies, the world looks four-dimensional. The compact dimensions can be thought of as a hidden instrument, shaping which notes the strings can play. Compactification is not unique, and that is where the landscape begins to form. There are many ways to choose the geometry of the extra dimensions, and each choice affects the spectrum of particles and forces in four dimensions. The shape controls how strings vibrate, which determines masses, charges, and interaction strengths. Different shapes imply different effective laws, even if the underlying theory is the same. Some shapes preserve more symmetry, others break it. Some yield particle spectra that resemble the standard model, while others produce exotic matter or forces that would make our kind of structure impossible. The theory also contains higher dimensional objects, brains, that strings can end on or move around, and they add another layer of flexibility. Brains can carry gauge fields and matter content, changing what looks like the standard model at low energies. Their arrangement affects symmetry breaking and the number of particle families, and it can influence how forces unify at high energies. Visually, brains invite a different kind of imagery than particles. Picture sheets and membranes floating in a higher dimensional space, intersecting and separating, with strings stretching between them like taut filaments. Where brains meet, new kinds of matter can appear, and the low-energy world inherits the geometry's constraints. Then come fluxes, generalized fields that can thread the compact dimensions, like invisible lines of force trapped in a folded maze. Fluxes are quantized, meaning they come in discrete units rather than continuous values, because the compact space only allows certain topological configurations. Turning on different flux integers changes the vacuum energy and stabilizes certain geometric features. It is like locking the extra dimensions into different patterns, where each pattern is a distinct solution rather than a small perturbation. Fluxes can contribute to the effective potential that shapes the vacuum, and they can shift the cosmological constant up or down. In the landscape story, these discrete choices become a combinatorial engine for enormous variety. The parameters that describe the size and shape of the compact space are called moduli, and they are not small details. If moduli are unfixed, they behave like massless fields, which would create long-range forces we do not observe and would make constants drift over time. So viable vacua require moduli stabilization, mechanisms that give these fields masses and pin them to specific values. Stabilization often uses fluxes, brains, and non-perturbative effects, and the phrase non-perturbative matters, because it signals physics beyond simple series expansions. Effects like instantons or strong coupling dynamics can generate potentials that trap moduli. The result is a vacuum that is metastable, long-lived, and consistent with a universe that does not visibly change its constants every epoch. When these ingredients combine, the number of metastable solutions explodes, and the explosion is not a metaphor. Different geometries, different flux choices, different brane setups, different stabilized moduli values. Each combination can yield a vacuum with its own cosmological constant and its own low-energy physics. The count is often summarized as around 10 to 500 possible vacua. The number is not a precise census, and it is not meant to be read like a head count of planets. It is a signal that the space of consistent solutions may be astronomically large, large enough that rarity becomes plausible. Even if the true number is smaller or larger, the qualitative point remains. There may be far more possible worlds than any single mechanism could uniquely select. Here we have to clarify what vacuum means in this context, because the word is overloaded. It is not empty space in the everyday sense, and it is not a mere absence of particles. It is a solution of the theory where fields settle into particular expectation values, and the geometry takes a particular form, including the compact dimensions topology. The vacuum determines the particle spectrum and the coupling constants we measure, and it determines which symmetries are broken. It also sets the effective potential landscape that governs small fluctuations, which become the particles in detectors. In this sense, empty space is more like a medium with properties, and those properties are the laws we experience. In this picture, laws become environmental, and that is the conceptual pivot. The underlying theory may be fixed, but the effective laws depend on which vacuum a region occupies. Masses, force strengths, symmetry breaking patterns, and even the sign and size of L can vary, and what we call fundamental may be local. This reframes the dread from Chapter 1, because vacuum decay was a bubble that changes the vacuum state and rewrites the rules. The landscape implies there are many destinations, not just one deeper valley. A bubble could be a transition between two among countless vacua, each with different constants and different stability. The false floor is not one trap. It is a maze of floors, stacked and branching, with corridors that lead to unfamiliar physics. Some floors are shallow and fragile, others are deep and long-lived, and the path between them is governed by quantum tunneling and cosmological dynamics. The next question is how any vacuum gets selected in the first place, because a static list of possibilities does not explain why we inhabit one. We need a cosmic mechanism that populates the landscape, turning mathematical options into realized regions. Without such a mechanism, the landscape is a library with no readers and no history. Eternal inflation is one proposed mechanism, and it fits naturally with the imagery of decay. Inflation is a period of accelerated expansion driven by a high-energy vacuum-like state, and it smooths and flattens the universe on large scales. In many models, inflation does not end everywhere at once, because quantum fluctuations can keep some regions inflating. Some regions decay out of the inflating state, while other regions keep inflating, so the process continues without a global finish. That is the eternal part, and it is not eternal in time everywhere. It is eternal in the sense that the inflating volume keeps reproducing faster than it disappears. In that scenario, bubble universes nucleate within an inflating background, like droplets forming in a supercooled fluid. Each bubble is like a decay event from a false vacuum, echoing the bubble wall logic from Chapter 1. Inside the bubble, inflation ends locally, and a hot Big Bang begins, filling the region with radiation and matter. The bubble interior becomes a universe with its own vacuum state, and the wall becomes a boundary between different effective laws. From the outside, the bubble expands at nearly the speed of light, carving out a new region of spacetime. From the inside, the bubble can look like an open, expanding cosmos with its own history. The landscape provides the menu, and eternal inflation provides the sampling. And the pairing is what makes the multiverse feel like physics rather than myth. Different bubbles can land in different vacua because quantum transitions can drop the fields into different minima. The result is a multiverse of causally separated regions, each with different low-energy constants. Our observable universe would be one bubble, one patch, and the horizon becomes a kind of epistemic wall. We can map our patch with exquisite precision, yet other patches remain beyond causal contact. The multiverse, if real, is not far away in ordinary space. It is separated by the structure of space-time itself. This makes fine-tuning look less like design and more like conditional probability, and that shift is both powerful and unsettling. If L varies across bubbles, most regions expand too fast or collapse too soon for galaxies. Observers appear only where structure persists long enough to form complex systems, and that selection effect biases what can be measured. We measure a small L because only small EL permits the measurement, and the logic is circular in a specific, technical way. It does not predict a unique value, but it can make a small value unsurprising given the condition that observers exist. The question becomes statistical. Among observer-friendly regions, what values are typical? The same logic can be applied to other parameters, at least in principle, though the details are harder. If the Higgs scale varies across vacua, then only certain ranges permit stable atoms and long-lived stars, because particle masses and reaction rates depend on it. If quark masses vary, only some ranges yield stable hydrogen and carbon, and only some yield nuclear pathways that build heavier elements. The landscape turns tuning problems into selection problems, and it changes what counts as an explanation. Instead of why this number, the question becomes why this number given that we are here? That conditional clause, quietly inserted, reshapes the entire ambition of fundamental physics. This is where the documentary's tension deepens, because the origin of reality stops looking like a single event with a single inevitable outcome. It starts looking like a branching process, where many consistent stories unfold in parallel. The disturbing implication is not only multiplicity, it is that explanation itself changes character, from deduction to distribution. In a landscape, asking why this universe has these constants can become like asking why a particular planet has this weather, except the stakes are deeper. The answer may be partly historical and partly conditional on where you can exist. That does not feel like the old dream of physics, which was inevitability, one set of laws derived from first principles. Yet the landscape idea is not accepted as a settled conclusion, and that uncertainty is part of its drama. It is a proposal under pressure from fine-tuning, not a triumph with clean experimental confirmation. String theory itself lacks direct tests at accessible energies, and the landscape multiplies the difficulty by expanding the space of outcomes. If there are 10,500 vacua, predicting our specific low-energy world becomes hard. And hard here means something technical. The mapping from compactification data to observable parameters is complicated, and the number of consistent solutions can swamp the predictive power we are used to. The fear is not that the theory is wrong, but that it becomes too flexible to constrain. Critics argue that the landscape risks becoming unfalsifiable, because any observation might be matched by some vacuum somewhere. If that happens, the theory stops making sharp predictions, and it starts to resemble a framework that can accommodate anything. Supporters respond that the underlying framework is constrained, and not every low-energy world is allowed by consistency conditions. They also argue that cosmology and consistency conditions can still yield statistical predictions, even if unique predictions are rare. Some vacua may be far more common than others, and some transitions may be dynamically favored. The hope is that typicality, combined with observational constraints, can still generate testable expectations. The controversy is not just philosophical, and it is not merely about taste. It is about what counts as explanation in fundamental physics, and what counts as a scientific success. Is a probability distribution over vacua an explanation, or a retreat from deeper mechanism? Does anthropic selection provide insight, or does it end the search for symmetry and dynamics? The field remains divided because the fine-tuning pressures remain real, and because the alternative is not obvious. If you reject selection, you must find a mechanism that enforces small l and a light Higgs without delicate cancellation. That is a high bar, and it is one reason the landscape remains on the table. There are also technical uncertainties inside the landscape story, and they matter for credibility. Counting vacua depends on assumptions about compactification, flux choices, and stabilization methods, and small changes in assumptions can change the count dramatically. Metastability must be demonstrated, not assumed, and some constructions remain debated. Even the existence of stable de Sitter vacua in string theory remains contested in parts of the community, because building positive vacuum energy solutions with full control is difficult. Some arguments suggest such vacua are rare or inconsistent, while others propose explicit constructions that claim to achieve them. The debate is technical, but the implication is simple. The landscape's most relevant regions may be hard to pin down. Still, the landscape persists because it connects multiple puzzles, and it does so with a single conceptual move. It offers a way to think about the smallness of L without miraculous cancellation, by turning it into a selection effect. It offers a way to interpret metastability as one step in a larger network of vacua, rather than a singular accident. It offers a framework where the constants are not sacred numbers, but outcomes of a state, like phases of matter. In that analogy, water can be ice or vapor depending on conditions, and the laws of flow change with phase. The landscape suggests that what we call laws may be closer to phase-dependent behavior than we once hoped. That persistence brings us back to the opening hook in a new key, and the imagery tightens. If reality is balanced on a false floor, the landscape suggests there are countless floors. Some are higher, some lower, many are unstable, and many are long-lived enough to host histories that feel complete from the inside. The disturbing thought is not only that our floor could give way, it is that the floor was never unique, and uniqueness may have been a human expectation rather than a cosmic rule. When you stand on one floor, it feels like ground. When you see the maze, ground becomes contingent. In this widened frame, the word origin becomes slippery, and the documentary's title starts to sound literal. The origin is no longer a single beginning that fixes everything. It becomes a process that generates regions, each with its own effective laws, each stabilized by its own vacuum configuration. The multiverse is not one story. It is a branching archive of consistent realities, where consistent means mathematically allowed and dynamically reachable. Some branches may be short and sterile, ending quickly in collapse or runaway expansion. Others may be long, structured, and filled with stars that burn for billions of years. That does not make our world less real inside its own boundaries, and it does not dissolve the solidity of our measurements. It makes its reality relational, dependent on the vacuum state and the information constraints that hold it coherent. The constants become part of the boundary conditions that define what counts as an atom, a star, a clock. Stability becomes local and conditional, and that phrase carries a quiet threat. If the vacuum is metastable, then the rules persist only as long as the state persists. The same laws that allow chemistry and memory might be temporary, not in human time, but in cosmic time. The central question now has sharper teeth, because it touches the meaning of observer independence. If laws are environmental, then observer independence is limited, and not in a trivial way. Observers do not merely discover constants. They exist only in regions where constants permit observers, and that feedback changes what it means to explain a measurement. Reality becomes information-bound, because only certain informational structures can persist long enough to ask questions. A universe that cannot form stable records cannot host science, and perhaps cannot host observers at all. That observation is not mystical. It is a constraint on what kinds of physics can be witnessed from the inside. At the same time, physics demands discipline, and the documentary must keep its footing. We have to separate what is measured from what is inferred, because the difference is the boundary between science and story. We measure L in our sky, and we measure particle masses in our detectors, and those measurements are precise. We do not measure other vacua, other bubbles, or the landscape directly, and that absence matters. The landscape is an attempt to make sense of the measured tuning, not a confirmed map of reality's full architecture. It is a hypothesis that earns attention because it links disparate puzzles with one coherent framework. Yet even as speculation, it changes the stakes, because it changes what unique means. If the space of possibilities is huge, then uniqueness is not the default, and inevitability becomes a special claim that must be earned. The origin of reality may not be a single answer. It may be a distribution, a statistical story, where explanation is about typicality and selection. That shift sets up the next move of the documentary, and it does so almost inevitably. If reality is a set of possible configurations, what describes the whole set at once? If the universe is not one trajectory but many branches, what equation governs the wave function of the cosmos? The story turns from landscapes in space to a wave function over all configurations, and the camera in our minds pulls back again. Instead of asking which vacuum we occupy, we ask what it means for the universe to have a quantum state at all. We ask whether the origin is a boundary condition on that state, or whether boundaries are all there ever were. From here, the story turns toward quantum cosmology and the Wheeler-DeWitt equation. We stop asking which vacuum we occupy and start asking what it means for the universe to have a quantum state. We ask whether the origin is a boundary condition on that state, or whether boundaries are all there ever were. We have been treating the origin like a moment, a spark that starts a clock, and then the clock simply runs. But the closer physics gets to the beginning, the more the clock itself becomes uncertain, its face blurring as we approach the edge. Even the word beginning starts to wobble, because it assumes a timeline that may not survive the approach. General relativity gives us space-time as geometry, shaped by energy and momentum, with gravity not as a force, but as curvature. Quantum theory gives us fields and probabilities, even when space looks empty, because empty still seethes with fluctuations. Near the Big Bang, those frameworks collide, because densities and curvatures rise beyond classical control, and the quantum vacuum stops behaving like a quiet baseline. The same region that demands Einstein's equations also demands quantum uncertainty, and the two demands do not naturally agree. At ordinary scales, gravity is weak enough that space-time behaves like a smooth stage, and the actors barely notice the boards beneath them. At extreme scales, the stage becomes part of the cast, and the script becomes quantum. Geometry itself starts to jitter. If we want an origin story that is more than metaphor, we have to quantize gravity, or at least understand what replaces classical space-time. Otherwise, we are describing the first page of the universe with ink that dissolves at the margin. The need is not philosophical, and it is not optional if singularities are real, because singularities are not merely dramatic. Classical general relativity predicts geodesic incompleteness and divergent curvature at the Big Bang, meaning that the paths of particles and light rays simply can't be extended. Those infinities are not just large numbers. They are signals that the classical description has exceeded its domain, like a map that ends in blank paper. In the language of geometry, the manifold runs out of meaningful continuation, and physics loses its grip. When Einstein's equations drive curvature toward infinity, the mathematics is telling us something physical has been left out. In practice, infinities often mark an approximation breaking down, not the world literally becoming infinite. The Big Bang singularity is therefore less a thing and more a warning label, stamped onto the edge of classical reasoning. Historically, that is how progress often begins, when a trusted theory points, almost unwillingly, to its own limits. The Planck scale is the boundary where our usual separations fail, and where the familiar hierarchy of effects collapses. At about 10 rose to 35 meters and 10 rose to 43 seconds, quantum fluctuations of geometry cannot be ignored, because the energy required to probe such distances would itself curve space-time violently. If you try to localize an event too sharply, you concentrate energy, and the concentration threatens to form a tiny horizon. Even the idea of a fixed background spacetime becomes suspect, because the background is itself dynamical. There is no rigid grid to measure against. To picture this, imagine zooming into what looked like smooth fabric from far away, only to find a restless weave. Distances are no longer passive labels, because the metric that defines distance is now fluctuating. The question is no longer what happens in space and time, but what are space and time made of when the classical continuum stops being reliable? The visual is not a clean grid, but a trembling mesh, as if the ruler itself is breathing. Earlier chapters framed reality as metastable, balanced on a false floor of vacuum structure. Now the floor is not only unstable, it may not even be laid out in time, because time itself may be part of the construction. The question shifts from which vacuum we occupy to what it means for the universe to evolve, when evolution is usually defined by time. If time is part of the scaffolding, what does it mean to ask what came before the scaffolding existed? Quantum cosmology tries to apply quantum rules to the entire universe, not to a subsystem tucked inside a larger world. That move is dangerous because in ordinary quantum mechanics, we rely on external time and external observers, even when we pretend we do not. In cosmology, there is no outside laboratory, and there is no external clock, no wall calendar hanging beyond the universe. The usual Copenhagen comfort, where measurement happens somewhere else, has nowhere to stand. This is where the usual language of measurement starts to wobble. In the lab, we can separate the system from the apparatus, and we can treat the clock as classical. For the universe as a whole, there is no clean split, and the clock must be built from the same quantum ingredients as everything else. Even the notion of the observer becomes a physical subsystem, with its own degrees of freedom and its own limits. One canonical approach begins with general relativity written in Hamiltonian form, a reformulation that treats dynamics as motion through a space of configurations. You slice space-time into spatial geometries, stacked like successive hypersurfaces, each slice carrying a three-dimensional metric. The slicing is a choice, and the theory is built to make no slice privileged. No foliation is the true time. In this language, what looks like evolution can be redescribed as a different bookkeeping choice. Visually, it is like taking a loaf of bread and deciding how to cut it, knowing that different cuts are equally valid. Some slices are thick, some are thin, some are angled, and none are preferred by the underlying physics. That freedom is not a bug. It is the expression of relativity's central claim that coordinates are conveniences, not entities. The universe does not come with labels attached, and our labels do not command it. That symmetry is called general covariance, and it is the heart of relativity, even when it feels like a technical detail. Coordinates are not physical, and time labels are not absolute, because the same physical situation can be described by many coordinate choices. When you translate that into Hamiltonian language, you do not get a standard energy that generates time evolution the way you do in ordinary mechanics. You get a structure that treats time more like a gauge choice than a cosmic metronome. Instead, you get constraints, equations that must vanish for physical states, and they encode the fact that many descriptions are redundant. The most famous is the Hamiltonian constraint, which in classical form is roughly h equals 0, alongside momentum constraints tied to spatial diffeomorphisms. It does not mean the universe has no energy in a naive sense, like an empty bank account. It means the generator of coordinate time is a gauge constraint, enforcing invariance under reparameterizations. The bookkeeping parameter can slide, and the physics must not change. This is one of those moments where the mathematics carries a philosophical sting. In everyday physics, the Hamiltonian is the engine that pushes the system forward in time. In general relativity, that engine is chained to a constraint, because time evolution in a chosen coordinate is not an observable motion of the universe itself. What looks like motion may be a reshuffling of description, and the theory insists we take that seriously. Quantize that constraint, and you get the Wheeler-DeWitt equation, a proposal that emerged in the 1960s as physicists tried to weld quantum mechanics to the geometry of space-time. It arrived in an era when quantum field theory was proving its power, while gravity remained stubbornly classical in its formulation. Conceptually, it is written as h acting on psi equals 0, with operator ordering subtleties hiding behind the compact notation. Psi is the wave function of the universe, a function over configurations of geometry and matter fields, over what is sometimes called superspace, the space of all possible three geometries. The disturbing feature is simple and technical at the same time, and it lands with unusual force. There is no explicit time variable in the equation, no t waiting on the right-hand side. The wave function is not written as psi of configuration and time. It is written as psi of configuration, full stop, as if the universe were a static object in a timeless catalogue. The silence where time should be is not a typo, it is the point. In ordinary quantum mechanics, the Schrödinger equation tells you how states change with time, and the time parameter sits there like a metronome. Here, the fundamental equation looks frozen, like a static condition rather than a dynamical law, because it resembles an eigenvalue equation with 0 on the right. The origin story starts to look like a category error, because the deepest description does not contain a ticking parameter. No universal before and after are built in. If the rulebook has no clock, what exactly is an initial condition? This is sometimes called the problem of time, and it is not a word game or a complaint about notation. In general relativity, time is part of the dynamical geometry, not an external parameter that can be held fixed. When you quantize the geometry, the time you wanted to use as a parameter becomes an operator-like degree of freedom, tangled with the rest of the quantum state. The very tool you used to define evolution becomes part of what must be evolved. So the Wheeler-DeWitt equation is not missing time by accident, as if someone forgot to include it. Time drops out because the theory refuses to privilege any coordinate choice. and because the Hamiltonian is enforcing gauge symmetry rather than generating physical change. The price of that symmetry is that evolution in coordinate time becomes gauge, and physical states satisfy a constraint that looks timeless. The reward is consistency with relativity's deepest principle, even when that consistency feels unnerving. If that sounds abstract, translate it into a metaphor that keeps the logic intact, because metaphors can clarify without softening the bite. Imagine the universe not as a movie, but as a complete map, drawn in full and folded into itself. A movie is defined by frames, ordered by an external projector, and the projector's rhythm is not part of the film. A map is defined all at once, with relationships encoded internally, and the order you trace across it is your choice. The map does not play, yet it contains every route. A timeless wave function is closer to the map than the movie, because it encodes correlations rather than a privileged sequence. It contains correlations between possible configurations, including configurations that look like different moments, different nows, different stages of cosmic history. What we call time becomes a way of reading those correlations from within, like following contour lines and calling them a journey. The drama is not in the ink, but in the path an embedded reader can take. In this view, the universe does not evolve in an external time, because there is no external time to evolve within. Observers inside the universe experience sequences because they track change relative to internal degrees of freedom, using some physical process as a reference. The feeling of flow is produced by comparing one part of the map to another, and by noticing that some correlations behave like reliable records. The present is not a universal slice. It is a local perspective stabilized by memory. The metaphor becomes vivid when you imagine a camera moving across a static landscape. The landscape does not happen, yet the camera's path produces a story, and each frame depends on where the camera is pointed. In quantum cosmology, the camera is an embedded subsystem, and its pointing is a pattern of correlations that can be stable or fragile. If the correlations decohere, the story sharpens. If they do not, the story blurs. This is the core idea of emergent time, and there are several technical routes to it, each with its own compromises. One route uses a semi-classical approximation, where geometry is treated as heavy and slowly varying, like a massive background that resists quantum jitter. Matter fields then evolve relative to that approximate background, and an effective time parameter appears. Not fundamental, but functional. It is the same move we use elsewhere in physics. Treat the heavy part as a clock for the light part. The approximation is not magic, and it has a clear structure that can be stated without drowning in equations. You write the wave function as something like a rapidly varying phase for geometry times a slower factor for matter, in a Born, Oppenheimer-like separation. In the limit where the gravitational part behaves classically, the matter part satisfies an approximate Schrödinger equation with a time parameter defined by the classical gravitational trajectory. The clock is not inserted, it is extracted. Time emerges as a parameter along classical gravitational trajectories in configuration space, where the phase of the gravitational wave function plays the role of an action. It is not fundamental. It is derived from the phase structure of the wave function, and it works only when the geometry behaves coherently. The same timeless equation can yield an effective time for subsystems, when one degree of freedom plays the role of a clock, and the rest are treated as evolving relative to it. When coherence fails, the clock loses its authority. This is why cosmology can look ordinary long after the Planck era, even if the fundamental equation is timeless. In a large, expanding universe, the scale factor can behave monotonically for long stretches, and that monotonic behavior supports a practical notion of later. But the emergence is conditional, and the condition is precisely what breaks near the beginning. The closer you get to the regime of violent quantum geometry, the less reliable the notion of a single, global time becomes. Another route is relational time, where you choose an internal variable and use it as a reference, because coordinate time is not an observable. You do not ask what the system does at time t, as if t were a universal label. You ask what one variable does when another variable has a certain value, turning time into a correlation statement. In plain terms, you trade when for while. This is not a mere reinterpretation. It is a different way of defining observables, and it matches how generally covariant theories hide their physical content. In a generally covariant theory, gauge invariant quantities are often relational, because absolute labels can be transformed away. They describe correlations between fields, not values at coordinate labels, and those correlations are what remain when redundancy is removed. The physics lives in relationships, not in coordinates. An internal clock can be a matter field, a scale factor, or any monotonic variable in a regime, including a scalar field rolling down a potential. The clock is not perfect, and it can fail near turning points or quantum regions where monotonicity breaks or fluctuations dominate. But in semi-classical domains, it can be good enough to recover familiar physics, including approximate conservation laws and causal ordering. The clock is an emergent tool, and tools have operating ranges. So the Wheeler-DeWitt equation can be timeless at the top level, yet time can appear in the middle, where effective descriptions become valid. That middle is where we live, where decoherence is strong and records persist, and where the universe looks like a sequence of classical events. The documentary's central question returns in a sharper form, because stability now includes temporal stability, whether the very notion of before can be trusted. If the clock is emergent, what keeps it from stuttering? If time is emergent, what anchors the arrow of time we actually experience? The sense that the past is fixed and the future is open. Physics at the microscopic level is often time reversal symmetric, at least in its fundamental equations, even when solutions look asymmetric. Yet macroscopic life is built on irreversibility, memory, and increasing entropy, and those are not optional features of experience. The arrow is not a decoration, it is the spine of every story we tell. The arrow of time is visible in the simplest scenes. Ice melts, smoke disperses, stars burn their nuclear fuel, and information spreads into the environment in ways that are hard to reverse. The equations allow reversal in principle, but the conditions required are so special that they almost never occur, and that almost never is the statistical heart of the arrow. The more particles involved, the more impossible the reversal becomes in practice. In quantum cosmology, the arrow is usually tied to boundary conditions and entropy gradients, because the laws alone do not pick a direction. A low entropy condition in one region of configuration space makes typical histories look like entropy increases away from it, in both directions that can be defined internally. The arrow is not inserted as a new law. It is inferred from an asymmetric condition that makes one direction rich in stable records. Why should the universe contain such an asymmetry at all? This reframes the origin again, because the origin becomes less about a first moment and more about a special boundary condition on the universe's state. The question shifts from what happened first to why the state is such that histories with arrows are typical rather than rare. It also raises an uncomfortable possibility. Perhaps beginning is just the name we give to the low entropy anchor, not a literal first frame. If so, the past is not a place we travel to, but a constraint we infer. Decoherence plays a supporting role in making time feel real, because it explains why we do not see quantum superpositions of macroscopic histories. When subsystems interact with many degrees of freedom, phases become effectively inaccessible, dispersed into correlations with the environment. The result is branching into quasi-classical histories that do not interfere, which makes records stable and gives events an apparently definite outcome. The world hardens into a particular story because interference becomes unreachable. Decoherence is sometimes described as the loss of quantum weirdness, but that description is too casual. The quantum state does not collapse in the fundamental equations. Rather, interference becomes practically unrecoverable for local observers. What remains are robust patterns, pointer states, that behave classically because they are continually monitored by their surroundings. The environment is not just scenery. It is a relentless witness. A record is an informational structure that correlates with a past configuration, and it can be as humble as a scratch in stone. Memory is not a mystical faculty. It is a physical pattern stored in matter, maintained by energy flow and protected by redundancy. The arrow of time is the direction in which such patterns can accumulate without being erased by typical dynamics, because erasure requires delicate coordination. To erase perfectly, you must gather dispersed information, and dispersion is what entropy likes. In a timeless framework, records are part of the map, not something added later by an external historian. The wave function contains correlations that look like fossils, photographs, and brain states, all embedded as consistent structures. We interpret those correlations as evidence of a past because we are embedded in the correlated structure, and because our own internal states function as records too. The past is the part of the map that contains reliable traces. That embedding is where the disturbing tone becomes personal, because it touches the machinery of identity. If the fundamental description is timeless, then the flow of time may be perspectival, a viewpoint-dependent feature of certain branches. It may be a feature of how certain subsystems read correlations, not a feature written into the universe's base layer. And that is a colder thought than it first appears. What feels like me moving forward may be a pattern consistently correlated. This does not mean time is an illusion in the trivial sense, like a mirage that disappears when you look closely. It means time may be emergent in the same way temperature is emergent, and emergence can still be objective within its domain. Temperature is real for gases, yet it is not a fundamental variable of the microstate, and it becomes meaningless when the system is too small or too far from equilibrium. Likewise, time can be real where the conditions for clocks and records are met. The analogy has limits, but the message is sharp, and it forces a choice of attitude. If you demand time at the deepest level, the equations do not obviously provide it, and the demand may be misplaced. If you accept emergence, you must explain why emergence is so robust that it feels unavoidable, and why it produces a consistent arrow rather than a chaotic flicker. Why is our branch so stable that it can host long memories and long predictions? Now connect this back to fine-tuning and the landscape pressure from earlier chapters, because the grammar of explanation is shifting again. If the universe is described by a wave function over configuration space, then a history is not selected by a dynamical roll through time, as if the cosmos were a ball rolling down a hill. A history is encoded as a pattern within a solution, and selection becomes a question of which correlations are realized in a branch. The why of cosmology becomes less mechanical and more structural. So the question of origin changes its grammar, and the change is more than rhetorical. Instead of asking why this happened, you ask why this solution, why this particular structure in the space of possible structures. Instead of asking why these initial conditions, you ask why the wave function has support on these correlations, and why those correlations contain stable observers. Explanation starts to sound like geometry, not like cause. In the landscape picture, we asked why our vacuum among many, and we worried about selection effects and anthropic filters. In quantum cosmology, We ask why our branch among many within the wave function, and why decoherence carves the state into the classical-like alternatives we inhabit. The multiverse becomes not only many regions in space-time, but many quasi-classical histories in a single quantum state, layered like transparent sheets. The question becomes, which sheet are we reading, and why does it read so cleanly? That convergence is not a clean resolution, it is a tightening knot, because it moves the mystery rather than eliminating it. The more we try to make the origin precise, the more it looks like a boundary condition problem, not a dynamical trigger. The origin becomes a constraint on the whole, not an event inside the whole. And that is a profound shift in what explanation even means. A cause inside time is replaced by a rule about the entire map. Some proposals make that explicit by specifying a boundary condition for the universe's wave function, and they come with striking visual imagery. The Hartle-Hawking no-boundary idea treats the beginning as a smooth closure in imaginary time, like a rounded cap rather than a sharp edge. The Vilenkin tunneling idea treats the universe as nucleating from a quantum regime, as if a classical space-time emerges by tunneling into existence from a classically forbidden region. In both cases, the singular point is traded for a quantum prescription. Historically, these ideas grew out of a broader attempt to tame the singularity without simply declaring it unphysical. Euclidean methods, path integrals, and semi-classical instantons offered a language in which beginning could be replaced by a geometrical condition. Yet each proposal carries assumptions about what counts as a permissible geometry, and about how probabilities should be assigned to entire universes. Even the word probability becomes delicate when there is only one universe to talk about. These are not settled answers, and they are not universally accepted, even among experts who agree on the problem. They are attempts to replace a singular beginning with a quantum condition, and to make sense of the Wheeler-DeWitt framework without smuggling in an external clock. They show how the word origin can survive, but only by changing meaning, turning from a moment into a boundary rule. The beginning becomes a condition of consistency, not a flash in time. Even if one boundary condition is chosen, the Wheeler-DeWitt equation remains a constraint, and the timelessness does not evaporate. The wave function is still timeless in its fundamental form, and the theory still refuses to privilege a global time variable. The narrative we experience is still something read off from correlations, not driven by an external clock. And that means history is a derived concept. The film is a way of reading the map, not a separate object. This is where the documentary's opening hook returns with a new twist, because the instability we feared becomes more subtle. If reality is balanced on a false floor, the collapse might not be something that happens in time, like a disaster arriving on schedule. The more disturbing possibility is that time is part of the flaw, and it can fail as a concept, leaving no schedule at all. What would it mean to fear an event if event is not fundamental? If the vacuum can decay, we feared a bubble wall arriving without warning, rewriting physics faster than light can outrun it. If time is emergent, the deeper fear is that warning itself depends on the structure that could change, because warning presumes an ordered sequence. The capacity to anticipate is a temporal structure, and temporal structure may not be fundamental, which makes the fear harder to even formulate. The threat is not only destruction, but the loss of the grammar that describes destruction. The central question becomes sharper and colder, because it now touches the status of objectivity. Is reality stable and observer-independent, or is it metastable and information-bound, with observer built into the description? In a timeless quantum cosmology, observer independence is complicated, because observers are patterns inside the state, not external referees. Objectivity becomes an emergent agreement among records. An observer is not outside the wave function, looking in, and that is the point that refuses to be comforting. An observer is a correlated subsystem, stabilized by decoherence and by the persistence of records. And those records are physical structures with finite resilience. The world that feels external is the consistent environment that those records define, and consistency is an emergent achievement. If the records fail, the world's solidity can fail with them. So what is the universe made of, if not evolving space-time, if not a film strip unspooling from a first frame? The Wheeler-DeWitt equation suggests the primary object is a state on configuration space, a mathematical object whose arguments are geometries and fields. Geometry and matter are coordinates on that space, and time is a derived ordering within certain regions where semi-classical behavior allows it. The basic layer is not stuff in space, but amplitudes over possible spaces. Configuration space is not a place we can point to in the sky, but it can be visualized as a vast landscape of possibilities. Each point corresponds to a whole spatial geometry, plus the matter fields that live on it, and the wave function assigns amplitudes across that landscape. In that picture, motion is not literal movement, but a pattern of correlations that can be read as a trajectory when conditions are right. The camera move is an internal bookkeeping of relationships. That is the existential tension of this chapter, and it does not resolve into a neat moral. The deepest description may not contain becoming, only being, a static condition that holds everything at once. Yet our lives are built from becoming, from change, from the accumulation of memories that define identity. And those memories feel like proof that time is real. The proof is persuasive, even if it is local. If the flow is perspectival, then the origin is not behind us in a universal sense, like a point you could travel toward. The origin is a feature of how our branch is organized, a low-entropy anchor that makes a direction of explanation possible, and that direction is what we call the past. The past is not a place, it is a correlation structure, and we are one of its self-consistent patterns. We do not merely remember the past, we are part of the pattern that makes past meaningful. This does not remove dread, it relocates it, and relocation can intensify rather than soothe. The fear is no longer only that the laws could change, or that a vacuum decay could erase us without warning. The fear is that the framework in which change makes sense is contingent and could be emergent from something that does not care about narratives, including ours. The universe may not be hostile, yet it may be indifferent to the idea of a story. Now the transition has to move forward, because timelessness is not the end of the story, and it cannot be because we still need a constructive account. If space-time and time might emerge, we have to ask what they emerge from, and what principle controls the emergence. The next chapter turns toward a more radical claim, that geometry is built from information constraints, and that where may be encoded in what can be known. The question becomes not only what exists, but what can be stored and shared. The pivot is unavoidable once you accept a wave function of the universe, because the wave function is a book of correlations. If the fundamental object is a state and its correlations, then the boundary between regions becomes central, because boundaries determine what can be separated, measured, and recorded. That boundary logic leads directly to holography, where information on a surface can encode a volume, and where geometry begins to look like an accounting system. The shape of space starts to resemble the shape of information. So we leave the Wheeler-DeWitt equation with a final, unsettling summary, spoken slowly because it resists intuition. The origin may not be a first frame of a cosmic film, and it may not be a moment at all. It may be a condition on a timeless map, and our sense of time may be the way the map reads us, through correlations that feel like memory. And the more we learn to read those correlations, the more we realize they might also be reading us. From here, the story turns toward information-based foundations and the holographic principle. If reality has no single solid floor, perhaps its most basic layer is a boundary, and the boundary is made of bits, with space-time emerging as a consequence of how those bits can be arranged. We ended last chapter with a universe described by correlations, not by an external clock, and that shift was already unsettling. Now we push the same logic further, until space-time itself looks like a derived convenience, useful, stable, and familiar, but not necessarily fundamental. The ground beneath the story starts to feel engineered, as if reality is assembled from constraints rather than poured into a pre-existing arena. Classical physics treats space as a container and time as a parameter, like graph paper and a ticking metronome laid beneath events. In Newton's picture, the stage is fixed even when the actors change, and the laws simply play out on top. General relativity complicates that stage by making geometry dynamical, yet it still assumes a smooth manifold where points exist before anything happens. You can curve the stage, stretch it, or ripple it with waves, but the stage is still there. Quantum gravity keeps hinting that the container is built from something else, and the build has limits that show up when we push nature to extremes. The first crack appears where gravity is strongest, and information seems trapped, and the crack is not subtle. Black holes look simple from far away, dark spheres with clean orbits around them. Yet they force a new accounting of what can exist, what can be known, and what can be kept. In wide shots, we see a star field bending around an invisible mass, as if the light itself is being persuaded. The lensing arcs tighten into rings, and the background sky seems to smear into a warped halo. In close shots, the edge becomes a sharp boundary in our imagination, a surface that is not a surface, and a line that is not a line. In classical general relativity, a black hole is defined by mass, charge, and spin, and the rest seems to vanish. The no-hair idea is not just poetic. It is a statement about what outside observers can measure using gravitational and electromagnetic fields. Everything else seems erased behind the horizon, as if detail falls out of reality when it crosses that boundary. The horizon is not a physical wall, yet it behaves like a one-way membrane for signals, and that asymmetry becomes the seed of a crisis. Even light cones tip inward there, and the future direction itself points deeper into the hole. Then thermodynamics enters, and the erasure becomes a paradox that physics cannot ignore. Thermodynamics is not a decorative add-on, it is the discipline that survived every revolution by refusing to be cheated. If a black hole destroys information, entropy bookkeeping fails, and physics loses its most reliable constraint on what processes are allowed. The second law is not a preference, it is a statistical inevitability for large systems, and it has the weight of experience behind it. When you coarse-grain a system, the number of compatible microstates almost always grows, and that growth is what we call entropy. Jacob Bekenstein proposes a radical fix in the early 1970s, and it sounds almost heretical at first. A black hole must carry entropy, because otherwise dropping matter in would violate the second law for the outside world. Imagine lowering a hot cup of gas toward the horizon, watching its messy microstates disappear from view, and then trying to claim the universe's entropy has decreased. Bekenstein's point is operational and coldly practical. If entropy is missing, the accounting is wrong. He also argues that there must be a bound on how much entropy can fit into a region, because gravity punishes excess information with collapse. But what could black hole entropy possibly depend on if the interior is hidden and coordinates can be chosen in misleading ways? The entropy cannot scale with volume, because the interior is not an observable container in any simple sense. And even the notion of inside volume depends on how you slice space-time. It must scale with what is operationally meaningful, which is the horizon boundary that separates accessible from inaccessible information. The horizon is where causal structure changes, and causal structure is what observers actually live inside. The boundary is not just geometry, it is a rule about which questions can ever be answered. Stephen Hawking adds the missing piece by quantizing fields near the horizon, turning a classical boundary into a quantum machine. In quantum field theory, empty space is not empty, because fields fluctuate even in their lowest energy state. Near a horizon, those fluctuations are distorted by the curved space-time, and particle definitions become observer-dependent in a precise way. The vacuum for a freely falling observer does not match the vacuum for an observer hovering outside, because positive frequency depends on time slicing. Black holes radiate thermally, so they have a temperature and a real entropy, and what looked like perfect darkness becomes a faint, steady glow. Visually, the black hole is no longer a silent void, because the edge shimmers with a thin halo of emission. In animations, virtual particle pairs appear and separate, with one partner falling inward while the other escapes outward. The story is often told as a cartoon, but the real content is deeper. The horizon changes how quantum modes are split between inside and outside. Hawking radiation is not a trick. It is a consequence of quantum fields in curved space-time, and it forces black holes into the same thermodynamic category as ordinary systems. The spectrum is nearly blackbody, and that nearly is where the information debate later hides. The Bekenstein-Hawking formula is the shock that lands like a hard number. The entropy is proportional to horizon area in Planck units, not to the volume inside. Planck units are not arbitrary because they combine gravity, quantum mechanics, and relativity into a single scale where all three matter. The Planck length is unimaginably small, yet it sets the granularity implied by the formula, as if the horizon is tiled by fundamental pixels. Each pixel is not a literal square, but it signals a minimum bookkeeping density that nature seems to respect. Area scaling is not a small correction. It is a structural insult to classical intuition, and the insult is specific. It says the number of degrees of freedom in a region grows like a surface, even though the region looks three-dimensional. If entropy counts microstates, then microstates are not living in the bulk the way we imagined. The bulk begins to look like a summary, not a storage device, and the horizon begins to look like the true ledger. We are forced to ask whether inside is a meaningful place or a convenient narrative we tell ourselves. This is where the documentary's central question tightens, because the formula is not just about black holes. If reality is observer-independent, why does its information capacity depend on a boundary that observers can define, cross, and sometimes never return from? The horizon acts like a limit on what can be known and remembered, and it does so without asking permission. It turns geometry into an information filter, and the filter looks fundamental rather than accidental. The universe seems to care less about where matter is, and more about what can be distinguished. From this crack, the holographic principle emerges as a disciplined claim. The maximum information in a region is encoded on its boundary, measured in area, and the claim is a bound, not a metaphor. It says that if you try to store too many independent degrees of freedom in a volume, gravity responds. The response is not gentle, because above a threshold, the region collapses into a black hole, and the horizon area becomes the final accounting surface. The bound behaves like a law of capacity, a cosmic limit on how detailed reality can be in one place. The accessible analogy is a three-dimensional world described by a two-dimensional surface, like a hologram that seems to hold depth within a flat film. The point is not a cute picture. It is a bound in quantum gravity that survives serious attempts to break it. When we say encoded, we do not mean that someone is writing messages on a cosmic screen. We mean that the number of distinct physical states that can be realized without collapse is limited by boundary area. The boundary is where the theory can keep its books without contradiction. The principle says you cannot pack unlimited independent bits into a volume, even if you imagine arbitrarily fine classical fields. Beyond a limit, gravity forces collapse, and the boundary becomes the ledger that counts what is possible. This is not about human ignorance. It is about physical capacity, and that distinction matters. Nature refuses to allow more distinct states than the boundary can register, even in principle, even for an ideal observer. If that is true, then the classical picture of continuous fields contains too many degrees of freedom to be literally real. Holography reframes the earlier chapter's dread in a new language, because it suggests a second kind of fragility. The false floor is not only metastable vacuum, it is also finite information support, and finiteness is a kind of vulnerability. If the universe is a computation, it is not running on infinite memory. The memory is geometric, and geometry itself may be the memory's outward appearance, stable enough for stars, yet bounded enough to force loss and compression. What looks like space may be the interface of a deeper accounting system. To make holography more than a slogan, physics needs an explicit example with equations that can be checked. The best developed case is ADS-CFT, a duality with sharp mathematical teeth that emerged in the late 1990s. It grew out of string theory and the study of D-branes, but its impact spread far beyond its birthplace. ADS stands for anti-de Sitter space, a spacetime with constant negative curvature, and CFT stands for conformal field theory, a quantum theory with special symmetry. Historically, it arrives after decades of hints that black hole entropy and string microstates might be counting the same hidden structure. In this duality, a gravity theory in a higher dimensional bulk is equivalent to a quantum field theory on the lower dimensional boundary. Two descriptions, one physics, and the equivalence is not approximate in the idealized setting. The boundary theory has no dynamical gravity in the usual sense, yet it encodes black holes, horizons, and bulk geometry through quantum degrees of freedom. What looks like geometry in one language appears as strongly organized quantum behavior in the other. The duality is so strict that a calculation done on the boundary can reproduce the thermodynamics of bulk black holes. Visually, we can picture a vast, curved interior volume whose edge is infinitely far away in a particular metric, yet still acts like a boundary for the theory. On that boundary, we see a lattice of interacting fields, fluctuating and entangling, as if the bulk is being projected from their collective motion. The equivalence suggests that what we call space can be reconstructed from non-spatial data. The bulk is not added, it is inferred from boundary correlations, and inference is a different kind of existence. What would it mean to live inside an emergent inference and never notice the reconstruction happening? Distance in the bulk becomes a derived measure of how boundary degrees of freedom are organized, not a primitive ruler laid down by God. Geometry starts to look like a compression algorithm for entanglement, because entanglement patterns can be summarized as smooth shapes. In many holographic calculations, the entanglement entropy of a region on the boundary is related to the area of a minimal surface in the bulk. The bulk surface behaves like a geometric shadow of quantum correlation, and the shadow has measurable structure. When the boundary state becomes more entangled, the bulk tends to look more connected, as if correlation literally stitches space together. This is where the chapter's tone turns colder, because emergence is not the same as safety. If space is emergent, then the stability of space depends on the stability of the information pattern that produces it. Earlier, we feared vacuum decay rewriting masses and forces, and that fear had a cinematic violence. Now we face a deeper threat, that the stage itself is contingent on informational structure, and contingency is a quieter kind of terror. A world that depends on correlations can, in principle, be disrupted by changing how those correlations are arranged. ADS and CFT is not our universe in detail, and we should not pretend it is, because our cosmos appears closer to de Sitter than anti-de Sitter. Its value is conceptual, showing that space-time can be an output, not an input, in a fully consistent quantum framework. The lesson is that gravity can be dual to a theory without gravity, and that possibility redraws the boundary of what fundamental means. If one description has space and the other does not, then space is negotiable. The mind resists that conclusion, because we evolved to trust the stage more than the script. The documentary's hook returns in a sharper form, because the false floor now looks like code. If reality is balanced on a false floor, the floor might be a boundary code we cannot see, and yet we live on its consequences. We can watch galaxies drift and clocks tick, but we may be watching the output of a deeper bookkeeping system. The question becomes less about what exists and more about what is required to make existence coherent. What minimum rules must hold for a world to remain legible to anything inside it? The next step is to ask what stitches the code into something that feels continuous, because continuity is what our senses insist on. The most promising thread is quantum entanglement, the correlations that survive distance and defy classical explanation. Entanglement is not a force and not a signal, and it does not let you send a message faster than light. It is a constraint on joint outcomes, a structure that links subsystems more tightly than classical probability allows, even when separated by empty space. In the mathematics, the state space refuses to factor cleanly, and that refusal is the clue. Historically, entanglement was treated as a philosophical irritation, then as a laboratory curiosity, and finally as a resource. Einstein called it spooky action at a distance. But the spookiness is not action, it is coordination. When two particles are entangled, the full state is not a product of independent parts, and that non-separability is the key. In plain language, the universe sometimes refuses to assign separate, complete properties to separate objects. The irony is that what once looked like a flaw is now a candidate for the glue of space. In holographic settings, entanglement entropy on the boundary relates to areas of surfaces in the bulk, and that relation is startlingly geometric. The idea is that if you take a region of the boundary and ask how entangled it is with the rest, the answer can be computed by an area in the bulk. Geometry begins to track entanglement like a shadow, and the shadow is not arbitrary. It changes smoothly when entanglement changes, as if space-time is responding to bookkeeping updates. The equations do not merely decorate the idea, they quantify it. That connection invites a dangerous idea, because it turns correlation into architecture. If entanglement patterns change, the bulk geometry that represents them must change too. And change in geometry is what we normally call gravity. The story then pivots to a conjecture that sounds like science fiction, but is built from serious puzzles. It is called ER equals EPR, and the name is a deliberate collision of two old ideas. It is also a reminder that physics sometimes advances by daring to connect structures that were once kept separate. EPR refers to entangled pairs, the Einstein, Podolsky, Rosen correlations that bothered Einstein because they challenged local realism. ER refers to Einstein, Rosen bridges, wormhole-like connections in space-time that appear as solutions to general relativity. The conjecture proposes that entanglement and wormholes are two languages for one underlying relation. An entangled pair may be connected by a non-traversable geometric bridge, not as a tunnel you can use, but as a geometric representation of shared quantum state. The bridge is a picture of unity, drawn in the ink of geometry. Visually, we can show two particles drifting apart through darkness, while a faint, ghostly throat forms between them in a separate layer of imagery. The bridge is not a shortcut through ordinary space, and it does not let you cheat causality. This is not a claim that you can travel through the bridge or send messages faster than light, because the wormholes involved are non-traversable in the simplest versions. The bridge is a bookkeeping of correlation, not a tunnel for signals, and the difference is the difference between fantasy and physics. The image is seductive, but the rules remain strict. ER equals EPR is not proven, and the chapter must keep that honest, because conjectures can seduce. It is a proposal that gains plausibility because it resolves tensions around black holes and information, especially the question of what happens when a black hole evaporates. Hawking's original calculation suggested radiation is thermal, and thermal radiation looks informationless. If a black hole evaporates completely, the naive story seems to turn a pure quantum state into a mixed one, and that violates quantum unitarity. Unitarity is not a philosophical preference. It is the rule that quantum evolution preserves total information. If a black hole evaporates, where does the information go? And how could it escape a horizon that forbids return? If it is preserved, it must be encoded in subtle correlations among the emitted quanta. Correlations too delicate to see in a coarse thermal spectrum. In modern language, the radiation may look thermal locally, yet globally it can carry entanglement structure that stores the missing details. Entanglement becomes the carrier, and the carrier must be tracked across time. The puzzle becomes a question about how correlations are redistributed as the horizon shrinks. The conjecture suggests a geometric way to picture that carrier, which is why it grips the imagination. The black hole interior may be tied to radiation by an entanglement structure that looks like a bridge, linking what fell in to what escaped. The bridge is not a literal hallway, but it is a way to visualize how inside and outside might remain part of one quantum system. When we say interior, we may be naming a region that is partly defined by entanglement itself. The boundary between regions becomes less like a wall and more like a cut in a quantum state. This reframes the meaning of separation, because separation becomes multi-layered. Two systems can be far apart in ordinary space, yet close in the entanglement graph that defines emergent geometry. Distance becomes less about meters and more about mutual information, which measures how much knowing one system tells you about another. Space becomes a relational metric, not an absolute container, and that is a conceptual inversion. If the metric is relational, then what we call far may sometimes be a misunderstanding. Now the narrative tension rises on purpose, because the implications are not merely academic. If geometry is woven from entanglement, then changing informational relationships can literally reshape what space is, at least in the emergent sense. That does not require exotic technology. It is already happening whenever systems interact and decohere, because interactions spread entanglement. The universe is constantly rewriting its entanglement map, and the rewrite is part of what we experience as time's unfolding. We feel time as change, but the deeper story may be the reorganization of correlations. In that map, horizons are not only gravitational surfaces, and they are not only artifacts of black holes. They are also information boundaries, places where correlations are limited and where entropy concentrates. And the limitation has physical consequences. A horizon divides degrees of freedom into those that can influence an observer and those that cannot. and that division affects what can become a record. Even cosmological horizons, set by accelerated expansion, impose similar limits on accessible information. The sky itself can become a boundary, not because of walls, but because of causal structure. This connects back to the landscape and vacuum selection problem, because laws and information capacity are not separable. If different vacua correspond to different low-energy laws, they also imply different information structures, different spectra of particles, and different ways entanglement can spread. Selection is not only about which constants you get, it is also about which informational architecture can stabilize a space-time that supports records and observers. A universe that cannot maintain durable correlations may never host anything that can ask why it exists. The ability to store a history may be as fundamental as the ability to form atoms. The testability tension returns in a new form, and it deserves to be spoken aloud. Holography and ADS-CFT are mathematically precise, yet connecting them to our cosmology remains difficult, because our boundary is not an ADS boundary. Still, the chapter's claim is narrower and more defensible, because it is about recurring hints. Quantum gravity keeps pointing to boundaries, entanglement, and finite information as unavoidable ingredients, and the hints come from multiple directions. When different lines of reasoning converge on the same constraint, it becomes harder to dismiss it as taste. At this point, we have treated information like an abstract currency. Now we pay the bill because physics insists that information is physical, and physical things have costs. The key constraint comes from thermodynamics, not from philosophy, and it has the blunt clarity of an inequality. It is Landauer's principle, and it ties computation to heat in a way that can't be wished away. The principle is a reminder that bit is not just a symbol, it is a physical state of matter or fields. Landauer states that erasing one bit of information costs at least kT ln2 of energy, where T is the environment temperature. Erasure increases entropy elsewhere, because forcing a system into a standard state compresses phase space and pushes uncertainty out. The principle is not about the act of learning, it is about resetting memory, which is what makes memory reusable. When you force a system into a standard state, you dump uncertainty into the surroundings, and the surroundings warm, sometimes imperceptibly, but never for free. In the lab, the bound is tiny, yet the logic is universal, and it scales with the number of erased bits. Visually, we can show a single bit flipping into a fixed Z0, while a pulse of heat ripples outward through a material lattice. The heat is not a metaphor, it is microscopic motion, and it spreads because of statistical inevitability. This is the chilling link between information and irreversibility, because irreversibility is what makes records stable. To create reusable memory, you must pay with heat, and the payment cannot be negotiated away by cleverness. The universe does not allow perfect recycling of certainty. Computation can be done reversibly in idealized limits, and in principle, you can design logic that avoids erasure. But real observers need stable records, and stable records require error correction, resetting, and energy flow. Noise is not an accident, it is the default in a warm universe, and fighting it requires work. Every time a system is forced back into a known state, the entropy bill is paid somewhere else, usually as waste heat. Even biology, our own memory included, runs on this thermodynamic gradient, spending free energy to keep patterns from dissolving. So the cost is not a laboratory detail, it is a cosmic constraint that scales up with complexity. A universe that stores histories must export entropy, and that export shapes its arrow of time, because entropy flow distinguishes past from future. In plain language, remembering is expensive, and forgetting is part of the price. The arrow of time is not merely a psychological feeling, it is a physical gradient created by irreversible processes. The past is the set of correlations we can still read, and the future is the set we have not yet paid to stabilize. Now connect Landauer back to black holes, because black holes are the ultimate memory devices in the thermodynamic sense. They maximize entropy for a given region, and they hide microstates behind a horizon, making them inaccessible to outside observers. If the maximum information is proportional to area, then the maximum memory is proportional to area, and that is a geometric law. Reality's storage capacity is geometric, and geometry is not free because geometry is tied to energy and curvature. A horizon is not just a boundary in space, it is a boundary in what can be stored without contradiction. We can linger on the visual of a horizon again, but now the horizon is not just darkness. It becomes a shimmering grid of Planck-scale tiles, each tile representing a limited capacity for distinction. The interior, once imagined as a vast vault, becomes secondary because the bound is set at the boundary. The disturbing synthesis is now unavoidable because the pieces lock together without asking for our comfort. If the ledger lives on surfaces, then depth may be an emergent illusion, and the illusion may be the only way a finite system can feel spacious. If the universe is an information processing system, it pays a thermodynamic price for every durable fact, and durability is what makes a world feel real. Existence is constrained by bookkeeping. Entropy must increase somewhere, horizons limit access, and irreversibility is the tax that makes records possible. The tax is not moral, it is statistical, and it is enforced by the combinatorics of microstates. The more you demand stable structure, the more you must dump disorder elsewhere. The question is not whether the bill exists, but where it is paid and what it buys. This makes the central question feel personal, because observers live inside the constraints. If reality is metastable and information-bound, then observer independence is limited by what can be recorded and maintained in physical memory. Observers are not spectators hovering outside the ledger, and they are not exempt from the accounting. Observers are physical subsystems that must erase, reset, and dissipate to keep a coherent world model. And that means observation is an energetic act. Even the act of stabilizing a belief into a record has a thermodynamic footprint. The opening hook returns with a new menace, because the flaw has changed shape. If the flaw is information, then collapse could mean losing the correlations that make a world readable, not merely losing a particular arrangement of matter. In earlier chapters, the fear was a vacuum bubble, rewriting the rules too fast to warn us. A sudden edit to the laws themselves. Here the fear is quieter. That reality cannot even afford unlimited self-description, and that limitation may be built into the deepest structure. What if the universe's most fundamental scarcity is not energy, but distinguishable states? A universe that computes itself without cost would violate thermodynamics, because it would create ordered records without exporting entropy. A universe that stores every detail without loss would exceed holographic bounds, because it would require more independent degrees of freedom than a boundary can support. So something must give, and what gives is our classical expectation of a complete, observer-independent state. The world becomes relational, bounded and lossy, and loss is not a failure, but a structural feature. The unsettling thought is that completeness may be incompatible with consistency. Even the concept of locality starts to look negotiated, and the negotiation is subtle. If entanglement defines geometry, then locality is an emergent approximation that can fail in extreme regimes, like near horizons or in highly entangled states. In ordinary life, locality works so well that it feels absolute, because interactions are short-range and information spreads at finite speed. Yet, holography suggests that what is near may be a statement about correlation structure rather than raw spatial separation. The world may be local because most states we inhabit have the right entanglement texture, not because locality is guaranteed. That failure is not only theoretical, because the same pressure points keep appearing. Black hole evaporation forces the information question into the open, because it challenges unitarity and the meaning of interior. Cosmological horizons force a similar question, because they limit what any observer can ever access. Quantum measurement forces it again, because it asks when a possibility becomes a fact, and facts are the currency of records. Each puzzle is a different face of the same constraint. Reality must remain self-consistent under finite information and irreversible bookkeeping. We have arrived at a cliff edge in the narrative. If space-time is emergent from information, then measurement is not a side issue. It is a structural operation, and the operation has a cost. Measurement is how correlations become records, and records are what make a branch of reality stable enough to inhabit. Without records, there is no durable geometry to inhabit, because the geometry is tied to the persistence of informational relationships. The simple question becomes unsettling. What is a fact if facts must be purchased with entropy? Visually, we can show a wave of quantum possibilities collapsing into a single trail of marks, like frost forming a pattern that does not easily melt. The marks are not mystical. They are physical states stabilized by dissipation and redundancy. A record is a pattern that resists being overwritten, and resistance requires energy flow. If holography limits storage and land-hour prices erasure, then measurement becomes part of the universe's economic system. The world we experience may be the subset of patterns that can afford to persist. This is the transition we need for the next chapter, because the logic now points directly at interpretation. If reality is informational and relational, then the role of measurement becomes central, and interpretations become unavoidable, whether we like them or not. Next, we face the measurement problem directly, and we test the idea that facts are personal or relational. Cubism and relational quantum mechanics step in where classical objectivity breaks, offering frameworks that treat fact as something that happens to an agent within constraints. The question is not whether the universe is strange, but how it stays coherent while being strange. The chapter ends with one final accounting, and it is meant to linger after the screen goes dark. Reality may not rest on a solid floor, only on metastable states, informational boundaries, and relational facts that cost energy to maintain. The universe may be less like a stage and more like a ledger, balanced, limited, and always paying for the privilege of being definite. And if the ledger is fundamental, we are not merely watching the universe, we are entries in its books. We have treated reality like a structure with hidden supports and strict limits, and we have trusted that its beams carry a single shared weight. Now we test the hardest support of all, the idea of a shared fact that exists the same way for everyone. Quantum mechanics predicts with brutal accuracy, yet it cannot agree with itself about outcomes when we ask what is actually happening. The equations evolve smooth superpositions across time, while experience reports single results that feel final and unambiguous. The Schrödinger equation is unitary and continuous for isolated systems, meaning probabilities are conserved and evolution is reversible in principle. In the mathematics, the state vector rotates through Hilbert space with perfect bookkeeping, and nothing in that motion prefers one outcome over another. Measurement seems discontinuous, selecting one outcome from many possibilities, as if the smooth flow suddenly snaps into a definite record. This jump is not a small correction, because the post-measurement state is different in kind, not merely different in degree. This is the measurement problem in its simplest form. and it has haunted the subject since the 1920s. In the early decades, it was not a side issue, because the founders were building the rules while arguing about what those rules meant. One rule says everything evolves as a wave. Another rule says a wave becomes a fact. Yet the theory never tells us where that second rule truly begins. The formalism offers a recipe that works, but it withholds a clear physical trigger for the recipe's most dramatic step. In the lab, we pretend the split is obvious because the workflow demands it. The electron is quantum, the detector is classical, and the readout is definite. An LED flashes, a needle settles, a digital counter increments by exactly 1. The scene looks ordinary, almost boring, because the violence is hidden in the assumptions. Metal housings damp vibrations, cryostats hiss softly, and cables carry signals that we treat as unambiguous facts, even though they originate in microscopic probabilities. But the theory itself does not mark that boundary, and it never writes classical on any piece of matter. If detectors are made of atoms, they should also obey unitary evolution, and their internal components should also be able to superpose and entangle. A photodiode is electrons in a lattice, and a pointer is atoms in a rigid structure, and rigidity itself is quantum chemistry. The classical look is a behavior, not a separate substance, and the equations do not grant exemptions for convenience. So we face the cut between quantum and classical, a line that seems practical but not fundamental. We can move the cut around, system here, apparatus there, environment farther out, but we cannot remove it without changing something deep. Historically, this cut was treated as a pragmatic truce rather than a physical mechanism. Bohr emphasized the necessity of classical descriptions for communication, because experiments must be described in shared language and shared reference frames. Von Neumann formalized the measurement chain that pushes the problem outward, step by step. His analysis makes the discomfort precise, because each link, system, apparatus, observer, can be treated quantum mechanically, and the chain has no natural place to stop. Superposition is not a metaphor for ignorance, like a coin hidden under a cup. It is a physical state where alternatives coexist in the formal description, and the mathematics insists that the coexistence can produce interference effects. A particle can be in a superposition of paths through an interferometer, and those paths can recombine to create bright and dark fringes. The pattern depends on relative phase, which is a measurable relationship, not a poetic flourish. A spin can be in a superposition of up and down relative to an axis, and the phase between components can matter as much as the components themselves. Change that phase, and the statistics of later measurements change, even though no classical picture of half up makes sense. When we measure, we get one click, not a blur of clicks or a half-formed compromise. The question is, what in the theory turns coexistence into exclusivity? What turns and into or without leaving fingerprints? Even the language we use reveals the tension, because we talk about outcomes as if they were waiting in a drawer. Yet the formalism speaks in amplitudes and phases, and it only yields probabilities until a specific interaction produces a record. That record is physical, not abstract, because it is stored as correlations in matter. A bit in memory is a metastable arrangement of charges, and a mark on paper is a chemical rearrangement that resists being undone. Decoherence enters as the modern workhorse, and it does real explanatory labor that earlier generations lacked. It explains why interference disappears when systems entangle with large environments, and why quantum weirdness becomes hard to sustain at human scales. A measuring device couples to the system and to countless uncontrolled degrees of freedom. Air molecules, thermal photons, vibrations in the lattice. Phase information spreads into correlations we cannot track, and those correlations effectively scramble the delicate relationships that make interference visible. In technical terms, the system's reduced density matrix loses its off-diagonal terms in the pointer basis, because the environment carries away witch branch information. The reduced state of the system looks like a mixture, and it behaves as if it has collapsed because interference terms become practically inaccessible. The pointer basis is not mystical, and it is not chosen by taste. It is selected by the interaction Hamiltonian because certain states get monitored by the environment more strongly, and those are the states that become stable records. Visually, decoherence is like ink dispersing in water, except the ink is phase coherence, and the water is the environment's vast state space. The information is not destroyed, but it is diluted into so many microscopic correlations that no realistic observer can gather it back. Imagine a quiet lab bench under fluorescent light, where a single photon hits a mirror and scatters faintly into the room. That tiny scattering can be enough to leak witch path information into the air, and the interference pattern fades without any dramatic event. Decoherence explains why macroscopic superpositions are not observed in practice, even though the equations permit them. It explains the stability of pointer states and classical records, because certain robust states resist being smeared by environmental monitoring. This is why a detector's display looks stable, and why a measurement record can be copied and recopied without changing its content. The environment redundantly encodes the same information in many places, so multiple observers can check the record and agree. This redundancy is sometimes called quantum Darwinism, because certain records proliferate while others die out. The world selects the states that can be broadcast widely, and those are the states that become the shared furniture of experience. But decoherence does not select a single outcome, and this is the crucial point that often gets blurred. It replaces one pure superposition with an apparent ensemble of branches, and it explains why branches stop interfering rather than why one branch becomes the fact. The global wave function still contains all branches, including the branches where the pointer points left and the branches where it points right. Decoherence tells us why branches do not interfere, not why one branch becomes the unique story the universe must tell. So the measurement problem survives in a sharper form, because we can now separate two questions cleanly. We can get classicality without getting uniqueness, and we can get stable records without getting an absolute catalogue of outcomes. If we insist on a single, observer-independent outcome, we must add something beyond unitary evolution. We can add collapse dynamics that modify Schrödinger's equation, hidden variables that specify definite values, or many worlds that treat every branch as equally real. Each option carries a cost, and the costs are not merely philosophical. Collapse theories must specify when and how the collapse happens. Hidden variable theories must handle non-locality, and many worlds must explain why probability feels like uncertainty rather than bookkeeping. The cost also shows up in what we expect from explanation. Do we want a mechanism that picks a winner, or can we accept that winner is a perspective-dependent label, anchored to an interaction and its record? This chapter takes a different route. It asks whether the demand for a global outcome is the wrong demand. The pressure becomes obvious in observer chain thought experiments, where the mathematics is applied without mercy. If everything is quantum, then observers are quantum systems too, and their memories and notebooks are also physical degrees of freedom. Start with a system in superposition, like a spin prepared in an equal combination of up and down. Let a friend in a sealed lab measure it and record a definite result, writing up or down on a card and storing it in a drawer. The lab is not a cartoon box because it has walls, air, thermal noise, and the slow drift of temperature. Yet in the idealization, we imagine perfect isolation. as if the door were a boundary between two descriptions of the same world. From the friend's perspective, the outcome is settled, and the lab now contains a stable record. The friend can point to the card, repeat the measurement protocol, and feel the ordinary certainty that science depends on. That certainty is not a delusion, because it is supported by the same decoherence that stabilizes everyday facts. The friend's brain state, the ink on the card, and the photons scatter off the drawer all lock together into a robust correlation. From outside, Wigner can treat the entire lab as a superposed quantum state, because he has not interacted with it. In that outside description, the friend, the card, the drawer, and the air inside the lab are all entangled with the measured system. If Wigner measures in an interference basis, he can, in principle, detect coherence between the friend's outcome branches, at least in an idealized world. The friend's definite record becomes part of a larger superposition, and the very existence of the record is described differently depending on perspective. The visual is unsettling. A sealed room lit by a desk lamp, a pen resting on paper, a human hand frozen mid-note. Yet, from the outside, the entire scene is a single quantum object with multiple, incompatible narratives. The camera lingers on the door seam and the quiet indicator lights, because nothing on the surface announces the conceptual fracture. The strangeness is not in the props, but in the permission the equations give us to describe them in two incompatible ways. Now ask what counts as a fact, and ask it with precision rather than poetry. Is the friend's outcome a fact for the universe, or only a fact for the friend? An event that exists within one interaction history, but not as a universal entry. If quantum theory applies universally, both descriptions are allowed by the same equations. The friend has a definite result, and Wigner has a superposition of friend states, and neither description violates the formal rules. The tension is not just psychological or linguistic, and it is not solved by insisting that someone must be really right. It is a clash between two consistent applications of the same formalism, and the clash targets the classical idea of a single, shared reality. We can extend the chain, and the extension is where the discomfort becomes structural. Another observer can treat Wigner and the lab as a quantum system, and so on without a natural endpoint, because the theory offers no privileged final observer. If facts are absolute, the chain must stop somewhere, and we must name the stopping point as a law of nature. If the chain never stops, facts become relative to where you stand, relative to what you have interacted with, and what has left a record in you. This is where the documentary's central question tightens, and the earlier themes return in a new register. Is reality stable and observer-independent, or metastable and information-bound through relationships that can shift as interactions accumulate? Earlier chapters made space-time look like an emergent bookkeeping of correlations, rather than a pre-existing stage. Now measurement makes facts look like bookkeeping too, because what happened depends on which correlations have been established and stabilized. The disturbing possibility is not that physics is incomplete in a simple, fixable way. The disturbing possibility is that the universe has no single detached viewpoint, and that our craving for one is a classical habit rather than a physical necessity. We need to be careful about what is being claimed, because the words can outrun the mathematics. Quantum mechanics still constrains experiences with objective structure and shared regularities, and it still yields reproducible statistics across laboratories. Yet the theory may deny a global catalogue of outcomes that all observers must agree on at all times. It may allow multiple consistent accounts, each tied to an interaction history, and it may only demand agreement when histories connect. Notice the subtlety in that demand, because it sounds like a loophole until you test it. When observers exchange signals, compare notes, or physically interact, The quantum rules constrain what combinations of records can coexist without contradiction. Two interpretations take this seriously without declaring reality meaningless, and they do so in different ways. They keep the predictive core, while changing what a quantum state is supposed to represent in the first place. First is Cubism, short for quantum Bayesianism, which grew from the Bayesian view of probability as rational belief under uncertainty. It treats the quantum state as an agent's personal probability assignments for future experiences, constrained by the formal rules of quantum theory. In Cubism, the wave function is not a physical field spread across space like an electromagnetic wave. It is a tool an agent uses to manage expectations under uncertainty, and it summarizes what that agent is prepared to bet on. The Born rule becomes a normative constraint on how an agent should update beliefs across different possible measurements. It is not a window into an observer-independent wave of matter, but it is still a strict rule that prevents arbitrary assignments. In practice, the Born rule links probabilities for incompatible measurements, forcing coherence among an agent's expectations. It is a mathematical discipline that says, in plain language, that your bets must fit together, even when nature offers mutually exclusive questions. A measurement is an action taken by an agent on the world, like choosing a question to ask with a particular instrument. The outcome is the agent's experience, created at the moment of interaction, and it is not assumed to pre-exist as a hidden property. That sounds subjective, so the boundary must be stated precisely rather than left as a vibe. Cubism does not deny an external world. It denies that the wave function directly describes it, and it denies that there is a single, true wave function for everyone. The world pushes back with surprises, and that pushback is the anchor that keeps Cubism from dissolving into solipsism. The agent cannot choose outcomes, only assign probabilities, and then receive a result that may defy expectation. Different agents can assign different quantum states to the same system, and the theory allows that because the state encodes information and intention. They are not contradicting physics. They are encoding different information and different planned actions, and the Born rule disciplines both. Agreement is possible because agents can communicate and update, and because the world produces stable regularities that make learning possible. Objectivity becomes an emergent consensus built from shared experiences and consistent updating, rather than a pre-installed list of properties. Cubism reframes the measurement problem by relocating collapse into the logic of inference. Collapse is not a physical explosion in space-time. It is an agent updating probabilities after an experience, and the drama shifts from ontology to the structure of rational prediction. The price is philosophical and physical at once, because it removes a comforting image. There is no God's eye wave function that is the system's true state for everyone, and there is no universal ledger of outcomes written behind the scenes. The second framework is relational quantum mechanics, associated with Carlo Rovelli and developed as a response to the same pressure. It keeps the formalism close to standard quantum theory, but changes what properties mean and when they can be said to exist. In RQM, a system has no absolute state that floats free of all interactions. Properties are only meaningful relative to another system that has interacted with it, because interaction is what establishes the correlations that make statements true or false. A measurement is just an interaction that establishes a correlation, whether the interacting system is a scientist, a detector, or a stray photon. The outcome is a relational fact between the two systems, and it is not automatically promoted to a universal fact. So a spin is not simply up or down as a permanent label attached to a particle. It is up relative to this apparatus, down relative to that basis, undefined relative to a system that never interacted, and always constrained by the quantum rules. RQM makes the observer chain less paradoxical, because it refuses to demand a single state that everyone must share. The friend has a fact relative to the friend's memory, while Vigna has a different state relative to Vigna, and both are legitimate within their contexts. There is no contradiction because there is no single global state that both must share at once. Consistency is demanded only where interactions connect accounts, because only then do the relational facts become jointly testable. When Vigna later opens the lab and interacts with the friend, new relational facts are established, and the network tightens. The two descriptions must then mesh through the interaction, because the interaction creates new correlations that constrain what each can say. RQM does not say anything goes, and it does not treat reality as a free-for-all. It says facts are local to interactions, and the network of interactions constrains what can be jointly asserted. Much like overlapping maps must agree where they overlap. Both cubism and RQM deny observer-independent outcomes as a universal inventory, and both preserve the operational success of quantum mechanics. Neither view says nothing is real, and neither claims that physics is merely opinion. They say reality is not a single completed list of properties independent of all relations, and they say the wave function is not a godlike object that must be the same for everyone. Reality is structured, but the structure is in constraints and correlations rather than in detached attributes. This is the climax because it attacks the oldest comfort in physics, the one inherited from classical mechanics. Classical thinking assumes the world has properties whether or not anyone looks, and that measurement merely reveals what was already there. Quantum theory, taken seriously, suggests a different structure, and it does so with mathematical insistence rather than mystical suggestion. Properties are not pre-written. They are established in events of interaction, and the events are where the theory places its sharpest commitments. The word observer can mislead here, because it drags in psychology and consciousness too quickly. The observer need not be human. It can be any physical system that becomes correlated with another, and that correlation can be as simple as a scattering event. A detector, a molecule, a photon bath, a black hole horizon, each can function as an observer in the minimal sense. Any interaction that creates a stable record can count as a measurement event, even if no mind ever reads it. This links back to decoherence without letting decoherence pretend to finish the job, and the distinction matters. Decoherence explains why records stabilize and why interference becomes inaccessible, while interpretations explain what records mean and what kind of fact a record is. In these frameworks, the cut is not between quantum and classical, as if nature were divided into two substances. The cut is between systems that have interacted and systems that have not, because interaction is what creates the relational scaffolding of statements. The classical world becomes the dense region of the interaction network, where records are redundant and agreements are easy. It is the regime where many independent environmental channels carry the same information, making disagreement fragile and quickly corrected. The quantum world becomes the sparse region, where correlations exist without a single global narrative that everyone must share. It is where coherence can persist, where alternative descriptions can coexist, and where what happened can remain perspective-bound. Now connect this to information and space-time, because the earlier chapters have already prepared this move. If geometry emerges from entanglement and correlation structure, then relational facts are not an add-on, and they are not a philosophical garnish. They may be the raw material from which space-time is reconstructed, because space-time itself may be a summary of who is correlated with whom. The world may be built from interaction patterns, who can influence whom, who can share records, and how strongly those links constrain possibilities. Earlier, we treated boundaries as fundamental because they limit information and because horizons divide what can be known. Here, boundaries also define which facts can be jointly asserted, because facts require shared correlations to become mutually checkable. A horizon is not only a geometric surface drawn on a diagram of curved spacetime. It is a constraint on interaction, and therefore a constraint on shared reality, because it limits which records can ever be compared. If two observers are separated by a horizon, their accessible records diverge in a way that is not merely practical. A global outcome list becomes not just unknown, but physically unformulable, because no interaction can ever stitch the accounts into a single ledger. The same logic appears in cosmology, where the scale of the system removes the usual escape routes. There is no external observer of the universe, so the demand for a universal wave function with universal outcomes becomes suspect, and the old classical picture loses its foothold. This echoes the Wheeler-DeWitt lesson, where time itself becomes a subtle concept in quantum gravity. The universe has no view from nowhere, because there is no nowhere outside it, and the dream of an external narrator becomes a category error. So the measurement problem is not a technical nuisance at the edge of physics, like a leftover glitch in an otherwise finished theory. It is the place where physics admits it cannot keep classical objectivity without adding new structure, and it is where interpretation becomes unavoidable. We should not overclaim what follows, because exaggeration would be a betrayal of the very discipline we are trying to understand. These interpretations do not prove that reality depends on consciousness or that minds create the world, and they do not license magical thinking. They claim something colder and more structural, and that coldness is part of the shock. Facts are not absolute objects. They are relational events constrained by quantum rules, and the constraints are as hard as any law we know. That claim is disturbing because it changes what it means to exist, and it changes it without drama or spectacle. Existence becomes less like occupying a stage and more like participating in a network, where nodes and links define what can be said. The universe is not a container with things inside, arranged like furniture in a room. It is a web of interactions that continuously defines what can be said to be the case, and the definitions are updated as new correlations are forged. The opening hook returns with new teeth, because we now see what the hidden support might be. If reality is balanced on a false floor, the floor may be the assumption of detached facts, facts that exist identically for every possible observer. When that assumption gives way, nothing explodes, and the laboratory does not dissolve into fog. What collapses is the idea that there is a single story happening everywhere at once, written in a universal tense and readable from any angle. We still live in a world of stable tables and reliable clocks, and that stability is not an illusion. Stability is real, but it may be emergent from dense relational bookkeeping, where countless interactions reinforce the same macroscopic regularities. The metastability theme returns in a new form, and it lands closer to home than vacuum decay ever did. Not only vacua can be metastable, but objectivity itself can be a metastable achievement, robust under ordinary conditions, yet not fundamental in the deepest description. The scientific status tension from earlier chapters reappears, because interpretation can feel like a retreat from testable claims. Interpretations are not free fantasies, because they must reproduce the same quantitative predictions, and they must respect the same experimental constraints. Yet they differ in what they say the mathematics refers to, and that difference matters when we ask what the world is. The debate is about ontology under constraint, not about changing the data, and the constraints are set by a century of precision tests. This is why the climax matters, and why it belongs in a documentary about reality's foundations rather than in a footnote. If physics ends in relational structures and constraints, then the origin of reality is not a substance, and it is not a hidden classical core. It is a pattern of allowed correlations, a set of rules for how experiences and records can cohere, and how contradictions are prevented. The origin is a web, not a flaw, and the web is held taut by the born rule and by the architecture of interaction. Now we push the disturbing thread to its sharpest point, because the logic demands it. If there is no observer-independent catalogue of outcomes, the universe has no single final description, and the idea of a complete external summary becomes questionable. There are only partial descriptions tied to interactions, each valid within its relational domain. The totality is not a picture, it is the consistency conditions linking many pictures, and those conditions are enforced whenever interactions connect the accounts. That is not nihilism, it is a different kind of realism, one that locates real in resistance and constraint. Reality is what resists, what constrains, what forces probabilities to obey the born rule, and what prevents us from rewriting outcomes by will. But reality may not be a single narrative that can be written from outside, as if the universe were a book on a shelf. It may be a network that can only be lived from within, where every statement is anchored to an interaction history. This is where we transition to the final chapter. If physics reduces to relational constraints, we return to the oldest question we keep orbiting. Why is there something rather than nothing? And why does the web hold together at all? Leibniz's question returns, now sharpened by the loss of a view from nowhere, because even the notion of something has become relational. If facts are relational and time is emergent, then existence is not a given stage waiting to be populated. Existence is the persistence of a self-consistent web, maintained by lawful constraints that prevent the network from tearing into incoherence. The final chapter asks whether that web could have failed to exist, and what it would mean for physics to answer that at all. And it asks, quietly but relentlessly, whether explanation can ever step outside the very relations that make explanation possible. Leibniz asked it in 1714 with a clarity that still cuts through modern jargon. Why is there something rather than nothing? Picture the scene that produced the question. Europe in the early Enlightenment, clocks becoming precise, calculus still new, and nature increasingly described by law. Leibniz was not asking for a missing mechanism. He was asking why any mechanism, any law, any stage exists at all. We return to the opening dread, because physics never found a clean void that stays empty. Even nothing arrives structured, energetic, law-bound, and possibly unstable. The deeper we push the word, the more it behaves like a thing with rules. The vacuum is not blank space, it is the lowest state of quantum fields that fill the universe. In quantum theory, every particle is an excitation of a field, and fields do not switch off. They retain a ground state with irreducible jitter, fluctuations that can't be removed without violating uncertainty. On screen, empty space becomes a dark ocean under a microscope, with ripples that never settle. Virtual particle pairs flicker in and out as bookkeeping in perturbation theory, and the vacuum's energy shows up in measurable ways. The Casimir effect, for example, turns emptiness into pressure between metal plates, as if the void can push. Chapter 1 named that trapdoor the false vacuum, and the phrase is deceptively calm. A false vacuum is a local minimum of a field's potential, stable to small nudges, yet not truly lowest. It is like a ball resting in a shallow valley, safe until a rare jump carries it over a ridge. The Higgs field sets masses, and its potential may place us on a metastable ledge. The Higgs is not merely a particle we discovered in 2012. It is the signature of a pervasive field whose non-zero value gives quarks and leptons their inertia, and therefore gives matter its familiar stubbornness. The numbers hint at a knife edge, tied to the Higgs mass, the top quark, and running couplings. As energy increases, quantum corrections run the strength of interactions, and the Higgs self-coupling may drift negative. That technical drift translates into a simple fear. Our valley might not be the deepest. The uncertainty is technical, but the implication is existential, and the drama is in the silence. If the standard model parameters sit near the boundary between stability and decay, then longevity becomes contingent. The universe could be long-lived by luck, not by guarantee. A true vacuum bubble would not announce itself with light or sound, because it is not an explosion in space. It is a change of space's own state, a phase transition in the fields that define particles. The front outruns warning, and the rules inside may not support atoms, chemistry, or even familiar dimensions. Visually, the bubble is a perfect betrayal. No fireball, no glare, only a smooth, advancing boundary. Stars keep shining until the moment they do not, because the information that would warn them cannot travel ahead of the front. The end, if it comes this way, arrives as a rewrite. Then we widened the dread to the cosmological constant, the quiet term in Einstein's equations. It behaves like a uniform energy density of the vacuum, producing a repulsive effect that accelerates cosmic expansion. Observationally, distant supernovae and the cosmic microwave background agree. The expansion is speeding up. Quantum field theory predicts enormous vacuum energy, yet the cosmos accelerates as if the value is tiny. If you sum zero-point energies up to high scales, you get a number that is catastrophically large. The mismatch is not a factor of 10 or 1,000, but a gulf that makes our best tools look naive. Renormalization can hide infinities in particle physics, but gravity couples to the baseline. In non-gravitational experiments, only energy differences matter, so we can subtract a constant and move on. In general relativity, that constant gravitates, so the bookkeeping becomes physical. The discrepancy becomes a demand for cancellation beyond ordinary naturalness, and that demand feels like a clue. Something seems to be balancing contributions with absurd precision, as if multiple huge terms conspire to leave a tiny residue. We can compute the pieces, but we do not understand the reason for the near-perfect subtraction. Fine-tuning followed as a pattern, not a single embarrassment, and the pattern is what unsettles. Small changes in constants erase chemistry, galaxies, and long-lived complexity. Alter the electron-to-proton mass ratio, shift the strength of electromagnetism, or nudge nuclear binding, and stable atoms can vanish. On screen, a periodic table fades like a dying map. Then a galaxy fails to condense from its gas. The lesson is not that life is special. The lesson is that structure requires narrow corridors in parameter space, and physics does not yet explain why we occupy one. String theory offered a way to make fine-tuning statistical rather than miraculous. A landscape of vacua turns laws into environmental outcomes, with selection among many metastable options. Extra dimensions and fluxes can yield an enormous menu of low-energy constants, each consistent, each different. That move bought possibility at the price of certainty, and the trade is philosophical as much as technical. Predictivity becomes a question of distributions, typicality, and what counts as evidence. If many vacua exist, we must ask what makes our vacuum probable, or even meaningfully testable. Quantum cosmology then removed the last external reference frame, the last imagined outside observer. The Wheeler-DeWitt equation replaces time evolution with a constraint, and the universe's wave function sits timeless. In canonical quantum gravity, the Hamiltonian becomes a condition, and before and after stop being fundamental variables. Time returns only as an emergent bookkeeping of correlations, a way subsystems track change relative to each other. A clock is not a universal metronome. It is a physical system whose states correlate with other states, and those correlations can be read as duration. The arrow depends on low entropy boundary conditions, which the equations do not uniquely justify. We observe a past of lower entropy because records exist, because gradients exist, because memory can be written. Yet the fundamental laws are largely time-symmetric, so the direction feels imported rather than derived. Next, space-time itself began to look like a derived convenience, not the unquestioned stage. Holography ties degrees of freedom to boundaries, and black holes force area-based entropy. Bekenstein and Hawking taught us that a black hole's entropy scales with horizon area, not volume, as if nature counts information on surfaces. Adiesos CFT showed a gravity world equivalent to a boundary theory without gravity, and the equivalence is precise. A higher dimensional spacetime can be encoded in a lower dimensional quantum field theory, with no bulk gravitons required. Geometry can be reconstructed from entanglement, as if space is a compression of correlations. Visually, a three-dimensional world peels open to reveal a luminous boundary grid, where links brighten as entanglement strengthens. Distances shrink and swell as correlations change, suggesting that near and far may be emergent labels. The stage begins to look like a diagram that updates. ER equals EPR pushed the idea further, still unproven but hard to ignore. Entanglement may be the stitching that makes separation and locality approximate. The conjecture hints that wormhole-like connections and quantum correlations are two languages for one underlying relation. Then we paid the bill for information, because description is not free in a physical universe. Landauer's principle ties erasure to heat, making durable records a thermodynamic expense. To reset one bit, you must dump at least kT-ln2 of energy as waste heat, a minimum cost set by temperature. Facts are not free because memory must be reset and stabilized against noise. Any apparatus must resist thermal agitation, cosmic rays, and internal chaos, and that resistance consumes resources. The arrow of time becomes the trail of costs required to keep records coherent, because keeping a past is work. Finally, measurement attacked the last classical comfort, the idea of a single, detached account. Decoherence explains stable pointer states, yet it does not select a single global outcome. The environment monitors certain variables, suppressing interference between alternatives, but the formalism still contains all branches. Cubism and relational quantum mechanics offered a colder realism, one that refuses a God's eye ledger. Quantum states track expectations or relations, and facts become interaction-bound rather than universal inventory. A result is not a floating property. It is an event between systems, registered in a record. Now the road ends where it must, at the boundary of scientific explanation. Physics excels at modeling transformations within a framework, yet it struggles to justify the framework's existence. We can calculate how states evolve, how symmetries constrain, how probabilities distribute, but not why there is a rule book at all. We can ask why this vacuum, why this L, why these laws, why this wave function. Each answer becomes a deeper parameter, a boundary condition, or a selection rule. The why recedes, not because we are lazy, but because explanation in physics often means relating one regularity to another. Even the multiverse, if real, shifts the question rather than erasing it. Why a landscape at all, and why rules that permit any consistent branch? If there are many domains, we still face the meta-law that generates them, and the constraints that define what counts as possible. So Leibniz returns, sharpened by everything we learned about nothing. Nothing in physics is not absence. It is a state with structure and constraints. It has fields, symmetries, renormalization rules, and quantum limits that do not read like emptiness. If nothing already has laws, then the question changes shape, and it becomes more surgical. Why these constraints? Why this capacity for self-consistent patterns? Why this possibility of stable records? Why does mathematics seem to bite into reality? And why does consistency have teeth? Here, the conclusion refuses comfort, but it offers a reframing. Reality may not be a substance sitting on a single solid floor. The old image of bedrock, an ultimate material, an ultimate particle, an ultimate moment, keeps dissolving into deeper relations. Reality may be an active, constrained process that persists by consistency, not by brute mass. Information limits, symmetry constraints, and relational bookkeeping may be what hold a world together. In plain terms, what exists is what can keep agreeing with itself as it unfolds. Metastability becomes more than a threat of vacuum decay, and more than a plot device. It becomes a template for existence, where what lasts is what can remain self-consistent under pressure. A metastable state is not eternal, yet it can be long-lived enough to host complexity, memory, and meaning. Observer independence also becomes conditional, not absolute, and that is a hard sentence to accept. A fact is what can be recorded, shared, and kept consistent across interactions within finite capacity. If no record can be stabilized, then the fact cannot outlive the interaction that created it. That does not make reality imaginary, it makes it participatory, and participation is physical. The world resists us through hard constraints, conservation laws, quantum probabilities, thermodynamic costs, yet it becomes definite through networks of correlation that include our instruments and bodies. We are not outside reality looking in, because there is no view from nowhere. We are physical subsystems inside the accounting, paying costs to stabilize descriptions. Every observation is a coupling, every memory a physical trace, every explanation a pattern compressed into a brain or a machine. When we measure, we do not merely reveal a pre-written property waiting behind the curtain. We create a new relational fact, constrained by the born rule and anchored in a physical record. The click in a detector is not just knowledge, it is an irreversible mark, purchased with entropy. In that sense, the universe is not a finished book waiting to be read, with all pages already printed. It is a self-description that only exists as far as it can be consistently written. The text is the web of stable correlations, and the ink is thermodynamic irreversibility. This is the disturbing origin that survived every equation, because it does not offer a first moment. Not a hidden substance, but a fragile web of constraints that can cohere. The deepest layer looks less like a thing and more like a rule-bound activity, continuing because it does not contradict itself. The final callback is quiet, because the most violent possibility is silent. A bubble front could still be racing through the dark, rewriting the vacuum without warning. It would not roar. It would simply arrive, and the constants that permit our kind of structure might stop being true. Pair it with a quieter truth that is harder to unsee once you have seen it. Our certainty about a solid foundation was the illusion, and relationships were the load-bearing structure. What we called fundamental keeps turning into a boundary, a correlation, a consistency condition. If the web persists, a world persists, and we persist as participants in its coherence. If the web fails, there may be no time to be afraid. The dread is not only that the rules could change, but that the very idea of a rulebook may be the only flaw. Leibniz's question remains, but it now points somewhere different than a missing cause. The deepest why may be answered only by the fact that consistency can exist at all. Why should there be any self-consistent structure, any stable pattern, any lawful regularity instead of pure contradiction. And the final disturbance is also the final meaning, because it turns spectators into components. Reality is not a passive object. It is what happens when constraints, information, and relations hold. The universe endures as long as its accounting balances, and we are part of the ledger. We began by looking for bedrock and found a false floor, a vacuum that can tunnel, flip its fields, and rewrite chemistry without warning. We followed that dread into the universe's unpaid debt, a cosmological constant so tiny it looks like an impossible cancellation, yet it steers the expansion of everything. We widened the lens to fine-tuning and the landscape, where laws may be environmental, time may be emergent, and space-time itself may be stitched from information, bounded by horizons, paid for in entropy, and stabilized by shared records. Along the way, the black hole paradox taught us that boundaries remember. Holography hinted that inside is built from correlations, and ER equals EPR suggested that distance is not fundamental. It is negotiated by entanglement. Then the measurement problem forced the most unsettling turn. Because even when decoherence makes a world look classical, it does not grant a single observer-independent catalogue of facts. In relational and agent-centered readings, a fact is not a free gift from nature. It is an expensive local agreement, secured by interaction, limited by finite memory, and kept coherent only as long as the web holds. That is why the Higgs knife edge matters, and why the top quark mass debate matters. Because our stability claims depend on how we define mass, how we run couplings, and how far we trust the Standard Model's extrapolation. It is also why the vacuum energy mismatch matters, because if gravity really couples to the baseline, then our best theories are balanced on a precision that looks less like inevitability and more like selection. New symmetries could still appear, modified gravity could still soften the coupling, or the multiverse could still turn why into which. But each option shifts what an explanation even means. In quantum cosmology, the Wheeler-DeWitt equation erased external time and replaced origin stories with boundary conditions, probability measures, and the hard question of why the arrow points at all. The thread tying every chapter together is not merely instability, but contingency, because reality looks less like a thing and more like a metastable pattern of constraints that keeps redescribing itself consistently. So, is reality stable and observer-independent?